Picture a world that defies everything we know about day and night, a planet caught in a cosmic standstill, where one hemisphere is forever facing its star, bathed in the warm, unending glow of daylight, while the other side exists in the deep, permanent chill of an eternal night. This isn't just a scene from science fiction. It's a real, scientifically plausible type of world known as a tidally locked planet, and among them, some of the most captivating are what astronomers call eyeball Earths. These are planets so perfectly balanced in their orbits that they present a face of stark, breathtaking contrast, a landscape split between blazing heat and frozen shadow, where the very idea of a sunset is something completely unknown. The concept alone sparks a profound sense of wonder. It challenges our Earth-centric perspective and invites us to stretch our imaginations toward alien environments where the rules of time, climate, and even life itself are rewritten. Imagine standing on the Terminator line, the razor-thin border between perpetual day and endless night, looking out at a sun that never moves in the sky, fixed in place for all of time. What would it be like to live in a world without dawn or dusk, where your entire reality is shaped by which side of the planet you call home? The possibilities are as profound as they are mysterious, hinting at forms of existence and adaptation that we are only just beginning to understand. In the grand story of cosmic exploration, few ideas stir the soul quite like the hunt for habitable worlds beyond our own. We gaze up at the night sky and wonder, are we alone? Could there be other Earths orbiting distant suns, cradling oceans, atmospheres, and perhaps even life? As our technology advances and telescopes peer deeper into the galaxy, we're uncovering planets that don't just resemble home, they shatter our expectations entirely. Tidally locked worlds, and eyeball Earths in particular, represent one of the most fascinating frontiers in this search. They are extreme environments forged by gravitational forces, where the conditions for life would be unlike anything we've ever encountered. And yet, in their strange and beautiful geometry, they offer a compelling vision of what might be possible on the fringes of habitability. This journey into the unknown isn't just about cataloging exotic planets. It's about rethinking the boundaries of life itself, exploring how living things could evolve under a star that never sets, or survive in a hemisphere of perpetual ice. It's a story of cosmic balance, of delicate and dramatic contrasts, and of the sheer diversity of worlds that the universe has to offer. So, where do we begin to understand such extraordinary places? In this video, we'll take you on a voyage to the heart of these enigmatic worlds. We'll explore the science behind tidal locking, visualize the stunning and surreal landscapes of eyeball Earths, and delve into the latest research that suggests even these extreme environments could harbor the ingredients for life. You'll discover how the relentless sunlight on one side could create vast temperate bands, while the dark side remains a frozen wilderness, and how, in between, extraordinary ecosystems might flourish. From the atmospheric dynamics that shape these planets to the imaginative ways scientists are searching for signs of biology, we'll uncover why eyeball Earths aren't just astronomical curiosities. They are windows into the incredible adaptability of nature and testaments to the boundless creativity of the cosmos. So come along as we step into the light and shadow of these remarkable worlds. By the end of our journey, you may never look at the sky or the idea of home in quite the same way again. To understand these strange worlds, we first need to grasp the basic physics of tidal locking, a phenomenon that's far more common in the cosmos than you might think. In fact, we have a perfect example right in our own cosmic backyard, our moon. If you look up at the night sky, you'll always see the same familiar face of the moon, with its distinct patterns of Maria and Highlands. The far side, the so-called dark side, remained a mystery until spacecraft first photographed it in the mid-20th century. This isn't a coincidence, it's a direct result of tidal forces. Over billions of years, the Earth's gravity has subtly stretched the Moon, creating a slight bulging. This gravitational interaction acted like a brake, gradually slowing the Moon's rotation until it became perfectly synchronized with its orbit around our planet. Now, it takes the Moon the same amount of time to spin once on its axis as it does to complete one full journey around the Earth, which is why we only ever see one side of it. This same fundamental process is what creates the permanent daysides and nightsides of distant exoplanets, only on a much more dramatic and life-altering scale. When this same principle applies to a planet orbiting its star, the consequences are profound. The star's immense gravity exerts a tidal force on the planet, just as Earth does on the Moon. Over astronomical timescales, this force works to slow the planet's rotation, eventually locking it into a state of synchronous rotation. Imagine a ball on a string, swinging it around your head. The same face of the ball always points toward your hand. This is the essential state of a tidally locked planet. One hemisphere, the dayside, is subjected to the star's relentless radiation, creating a scorching, sun-scorched landscape where the sun never sets and hangs motionless in the sky. The opposite hemisphere, the nightside, is plunged into an eternal, deep-freeze darkness, utterly devoid of stellar light and heat. Between them lies a narrow, perpetual twilight zone known as the terminator line, a razor-thin band where the extreme conditions of both sides meet. You might wonder why we don't see this in our own solar system with planets like Mercury, which was once thought to be tidally locked to the Sun. The reality is more nuanced. Mercury is in a 3-to-2 orbital resonance, meaning it rotates 3 times for every 2 orbits around the Sun. True 1-to-1 tidal locking is most likely to occur for planets that are very close to their parent stars. And this is where the story gets particularly interesting for the search for life. The most common type of star in our galaxy is the red dwarf, also known as an M-dwarf star. These stars are smaller, cooler, and dimmer than our Sun. For a planet to receive enough warmth for liquid water to potentially exist on its surface to be in the so-called habitable zone, it must orbit extremely close to the star. So close, in fact, that the gravitational pull is immense, making tidal locking not just a possibility, but a near certainty. This means that the vast majority of potentially habitable real estate in our galaxy could be on these strange, synchronously rotating worlds where the climate is defined not by seasons but by geography. The very conditions that might allow for liquid water also create an environment of extreme and permanent contrasts, setting the stage for the emergence of the most fascinating of these worlds, the eyeball Earth. Now, let's bring this concept to life by visualizing the actual birth of an eyeball Earth. Picture a young, rocky planet, similar in size to our own world, orbiting comfortably within the habitable zone of a calm red dwarf star. This planet is a water world, its surface almost entirely covered by a deep, global ocean or a thick, encapsulating shell of ice. For a time, it might even rotate at a pace that gives it a familiar cycle of day and night. But the star's gravity is relentless. Over millions of years, this constant pull acts as a cosmic brake, gradually but surely slowing the planet's spin until finally it stops. The planet becomes tidally locked, and from that moment forward, its destiny is sealed, and its transformation into a celestial eyeball begins. The star's energy now bombards one hemisphere without pause. On the dayside, the unending sunlight pours down, its heat absorbed by the vast ocean. There is no night to provide a cooling period, no sunset to bring relief. The temperature begins to climb, and a monumental process starts, the Great Melt. If the planet began with an icy shell, it begins to thaw from the substellar point, the spot directly under the star radiating outward. The ice retreats, revealing a deep, liquid ocean that grows ever larger and warmer. This isn't a calm, placid sea. It's a dynamic, swirling body of water, churned by powerful currents and storms born from the extreme temperature differences. It becomes a warm, potentially life-giving ocean trapped under a perpetual, blazing sun. Meanwhile, on the opposite side of the world, a very different and equally extreme reality takes hold. The night side never receives a single ray of starlight. It is a land of absolute cold and profound darkness. Any heat that manages to travel from the dayside quickly radiates out into the void of space. The ocean here, if it was ever liquid, freezes solid. It becomes a global-scale ice sheet, a frozen wasteland that grows thicker and more permanent with every passing eon. This ice cap isn't like the seasonal ice at Earth's poles. It is a permanent, deeply frozen feature, likely many miles thick, representing one of the most stable and cold environments in the entire universe. The true magic, the moment the eyeball Earth gets its name, happens in the interaction between these two extremes. The warm ocean on the dayside and the frozen ice on the night side create a planet-spanning temperature gradient. This gradient drives immense atmospheric and oceanic circulation. Warm air and water from the dayside flow toward the cold night side, while frigid air from the dark side spills back toward the light. This constant exchange of energy and materials shapes the planet's final form. The dayside ocean does not spread to cover the entire planet because the cold from the night side is so intense that it acts as a barrier. The result is a world with a vast circular blue iris of open ocean on the dayside, surrounded by a white sclera of icy terrain that covers the rest of the planet, including the entire night side and often creeping into the Twilight terminator region. From space, the visual effect is unmistakable. The planet looks like a giant staring eye, a cosmic observer forever fixed on its parent star. This stunning appearance isn't just a curiosity. It's the direct and beautiful consequence of fundamental physics playing out on a global scale, creating a world of stark, stable, and breathtaking contrast. This permanent dayside is a world defined by relentless energy. Beneath the unmoving, brilliant glare of its star lies not a barren desert, but an astonishingly dynamic aquatic realm, a planet-wide ocean that never knows darkness. The sheer scale of this warm, liquid sea is difficult to grasp. It spans an entire hemisphere, a single, continuous body of water heated ceaselessly at its center and protected from the encroaching cold of the night side by powerful natural forces. This is not a calm, glassy pond. It's a churning, swirling cauldron of activity. The immense temperature difference between the scorching substellar point and the frigid terminator line creates a permanent, planet-spanning engine for weather. Howling winds, born from the high-pressure dayside rushing toward the low-pressure night side, whip across the ocean's surface, generating colossal waves that could dwarf anything experienced on Earth. These waves would travel for thousands of miles without ever encountering a coastline, building into monstrous, perpetual swells. Beneath the surface, the motion continues in the form of vast, powerful currents. Think of it as a global conveyor belt of water and heat. Warm water from the central, hottest regions flows outward, traveling toward the twilight zone. As it approaches the cold, this water cools, becomes denser, and sinks, only to be drawn back toward the warm center along deeper ocean pathways to be reheated and begin the cycle anew. This constant, vigorous circulation is vital. It prevents the dayside ocean from simply boiling away over eons by distributing the star's intense heat energy across a massive volume of water. More importantly, this churning acts as a planetary mixing machine, constantly stirring nutrients from the depths up toward the sunlit surface. On Earth, such upwelling zones are teeming with life, and here, that same process could be operating on a hemispheric scale, creating a potentially fertile soup of dissolved minerals and organic compounds bathed in perpetual sunlight. All of this liquid water, constantly warmed, leads to another dominant feature of the dayside, a thick, humid atmosphere rich with water vapor. The unending evaporation from the warm ocean surface would saturate the air, creating a permanent, planet-wide blanket of humidity. This vapor-rich atmosphere would have profound effects. For one, it would act as a powerful greenhouse blanket, trapping heat and helping to maintain the ocean's liquid state, effectively working with the ocean currents to regulate the planet's climate. But it would also create weather phenomena of an intensity we can barely imagine. The combination of extreme heat, abundant moisture, and constant atmospheric circulation could spawn permanent storm systems. Imagine a hurricane-like structure, not that spins and moves on, but one that is locked in place over the warmest part of the ocean, feeding on the endless supply of energy and moisture, potentially lasting for millions of years. The skies might be dominated by thick, swirling cloud banks, with torrential rainfall in some bands and clearer, hotter skies in others, creating a complex and layered meteorological tapestry. This brings us to the most captivating question of all. Could life exist in this strange, sunny sea? The conditions, while extreme from our Earth-centric view, actually meet several key criteria for habitability. There is, of course, an abundance of the universal solvent liquid water. There is a tremendous and constant source of energy from the star driving photosynthesis. And the constant oceanic and atmospheric churning provides a mechanism for recycling essential nutrients. Life here would not have to contend with the punishing cycle of freezing and thawing that a day-night cycle can impose. Instead, it would evolve in a stable, if intense, thermal environment. Photosynthetic organisms wouldn't be simple algae floating aimlessly. They might form vast, mat-like colonies on the ocean surface, engineered to handle the constant high-intensity light. They could develop sophisticated protective mechanisms against ultraviolet radiation, perhaps living just beneath the water's surface or producing their own biological sunscreens. The base of the food web in this eternal ocean could be incredibly robust, supporting a cascade of more complex life forms adapted to a world without darkness, where hunting, breeding, and migrating would follow rhythms based on ocean currents and temperature gradients, not the rising and setting of a sun. The dayside of an eyeball Earth, therefore, is not a hellscape but a world of staggering potential, a testament to how life might not just endure but truly thrive under a star that never sets. But if the dayside is a world of relentless, sun-drenched energy and the nightside a domain of frozen permanence, where does that leave the boundary between them? This brings us to the most intriguing and potentially habitable region of all, the terminator line, a narrow, ribbon-like band that wraps around the entire planet, forever caught in the balance between eternal day and endless night. Here, the sun perpetually sits on the horizon, casting a soft, diffused, golden twilight that never deepens into night and never brightens into day. It is a world of perpetual sunset, a place of stunning beauty and remarkable stability. While the dayside bakes and the nightside freezes, the terminator line exists in a kind of thermal sweet spot. The constant, low-angle sunlight provides just enough warmth to prevent the deep freeze of the nightside, but not so much that all the water boils away. This creates a band of potentially moderate, life-friendly temperatures, making the terminator one of the most compelling places in the entire universe to search for alien life. The very nature of this twilight zone would give rise to landscapes unlike any we know on Earth. Imagine standing on a shoreline within this band, looking one way toward the dayside. You'd see a vast, warm ocean stretching into the distance, its surface shimmering under the unwavering, brilliant star. Turn around and look toward the nightside, and you would be met with the towering, glittering cliffs of a global ice sheet, a wall of ancient, frozen water that could be miles high. The interaction between these two colossal forces, the warm ocean and the immense glacier, would create a dynamic and ever-changing coastline. The ice from the nightside would be in a constant, slow-motion flow toward the relative warmth of the terminator, calving gigantic icebergs into the liquid sea. These icebergs would drift into the twilight waters, slowly melting and releasing fresh water and any minerals trapped within the ice, potentially seeding the environment with the very building blocks necessary for life. This constant push and pull between ice and liquid would sculpt dramatic fjords, inlets, and frozen headlands, creating a coastline of breathtaking, stark beauty. Crucially, the stable conditions of the terminator could allow for large bodies of liquid water to persist on its surface. While the dayside has a planet-wide ocean and the nightside a global ice cap, the terminator might host everything from sheltered seas and sprawling networks of meltwater lakes to vast, slow-moving rivers fed by the gradual melting of the nightside ice sheet. These wouldn't be turbulent, storm-racked waters like those on the dayside, but calmer, more protected bodies, their surfaces often shrouded in a characteristic permanent mist. This mist would form as warm, moist air from the dayside flows into the cooler terminator zone, causing the water vapor to condense. This perpetual, ground-level cloud cover could act as an additional buffer, helping to regulate temperature by trapping warmth at the surface and shielding it from the cold blackness of space on the nightside horizon. Within these calm, liquid water environments, the conditions for biochemistry to begin and evolve are exceptionally promising. Life in this twilight world would need to be uniquely adapted to a very specific set of challenges and opportunities. The most obvious difference is the light itself. Instead of the intense, full-spectrum light of the dayside, organisms here would be bathed in a perpetual, reddish-gold glow, as the atmosphere scatters the star's light on its long path along the horizon. Photosynthetic life would need to be extraordinarily efficient, specialized in capturing these specific, low-energy wavelengths. We might see vast forests of alien vegetation not in vibrant green, but in deep shades of black or purple, pigments perfectly tuned to absorb every last photon of the dim twilight. These wouldn't be forests as we know them, but perhaps vast, sprawling mats of moss-like organisms clinging to rocky coastlines, or strange, towering fungal forms that derive energy from the chemical gradients between the land and the sea. For more complex, mobile life, the terminator would present a world of striking contrasts within a very narrow band. An animal living here would have a clear choice. It could venture a short distance into the dayside to bask in warmer temperatures and find more prolific food sources, but it would risk overheating and damaging levels of radiation. Alternatively, it could retreat into the colder, darker edges near the nightside to hide from predators or conserve energy, but it would face the threat of freezing solid. This would likely lead to highly specialized migratory behaviors, with creatures following strict vertical or horizontal paths within the band to maintain their ideal body temperature. The entire ecosystem could be structured along a precise thermal gradient, with different species occupying specific niches based on their tolerance for light and heat. The terminator line, therefore, is not just a line on a map. It's a complete, self-contained world, a thin ribbon of possibility where the fierce energies of light and dark meet, creating an oasis of stability that could very well be one of the most common cradles for life in our galaxy. While the dayside basks in endless light and the terminator thrives in perpetual twilight, the night side of an eyeball Earth presents a reality so alien it challenges our very understanding of a world. This is a hemisphere of absolute zero, a place where the concept of a sun is nothing more than a forgotten myth. Here, the darkness is not merely the absence of light. It is a physical, palpable force, a deep and permanent cold that has gripped the landscape for eons. The temperature plummets to hundreds of degrees below freezing, so extreme that the very air begins to freeze. Any atmosphere this world possesses, whether nitrogen, oxygen, or carbon dioxide, cannot remain gaseous in such profound cold. It condenses, crystallizes, and falls from the black sky as snow, a perpetual, silent storm that has been raging for millions of years. This isn't a weather event, it's a permanent state of being. The entire atmospheric envelope freezes solid, creating a global ice cap of unimaginable scale. We're not talking about the frozen water of the ocean alone, but a layer many miles thick composed of both water ice and frozen atmospheric gases, a crushing, monolithic shell that encases the entire nightside in a tomb of ice and silence. Beneath this oppressive, frozen crust, however, lies one of the most tantalizing possibilities in all of astrobiology. The surface is dead and locked in ice, but deep below, the planet's own inner fire offers a flicker of hope. Just like Earth, a rocky eyeball Earth would be heated from within by two powerful sources: the residual heat from its violent formation and the ongoing decay of radioactive elements in its core. This geothermal warmth constantly seeps up through the planetary crust. On the surface of the dayside or terminator, this heat is utterly insignificant compared to the power of the star. But on the nightside, where no stellar energy ever reaches, this internal heat becomes the dominant, life-giving force in the entire environment. It acts as a cosmic blowtorch, fighting a perpetual war against the cold from above. This heat can be powerful enough to prevent the entire ocean from freezing solid, melting a vast layer of water at the boundary between the rocky seafloor and the thick overlying ice shell. The result is a global subsurface ocean, completely encapsulated and hidden from the universe, a dark, aquatic abyss warmed from below by geothermal vents and insulated from the space like cold above by miles of solid ice. This creates an environment with a startling and profound parallel right here in our own solar system. Jupiter's moon Europa is a frozen world far from the sun's warmth, yet scientists are virtually certain it harbors a massive, global subsurface ocean beneath its icy crust, kept liquid by tidal forces and geothermal energy. An eyeball Earth's nightside offers a scenario that is, in many ways, even more stable and long-lived. This hidden sea would be utterly dark, devoid of any sunlight for billions of years. It would be under immense pressure from the weight of the ice above, and its chemistry would be shaped entirely by the minerals leaching from the seafloor and the energy from hydrothermal vents. These vents, similar to the black smokers found at the bottom of Earth's oceans, would spew superheated, mineral-rich water into the darkness, creating isolated oases of energy and potential nutrients in the vast, cold abyss. And this is where the question of life becomes utterly fascinating. Could biology find a way in this sunless, pressurized deep? On Earth, we have discovered entire ecosystems that thrive in the absolute darkness of the deep ocean, completely independent of the sun. These complex communities of tube worms, blind shrimp, and bizarre bacteria derive all their energy not from photosynthesis but from chemosynthesis. They use the chemical energy from hydrogen sulfide and other minerals erupting from hydrothermal vents to power their metabolisms. In the eternal night of an eyeball Earth subsurface ocean, an identical process could be taking place. Life here would not just be simple, single-celled organisms eking out an existence. In an environment that has been stable for billions of years, evolution could have plenty of time to work its magic. We might find vast fields of microbial mats coating the seafloor near warm vents, filter-feeding organisms anchored to the underside of the ice ceiling, or even free-swimming, predatory creatures that have evolved to navigate the pitch black using sonar or sensitivity to pressure changes. Their world would be defined by the slow, steady pulse of geothermal heat and the constant, gentle fall of marine snow or organic debris that might drift over from the dayside ocean through deep, slow currents that connect the two hemispheres. This would be a truly alien biosphere, a civilization of the deep that might never know that their planet has another side bathed in brilliant, unending light. Now, to truly grasp the climate of an eyeball Earth, we need to step back and view the planet as a single, interconnected system, where the atmosphere itself becomes a planetary-scale engine driven by one overwhelming force: the extreme temperature difference between its two halves. This isn't just a mild pressure gradient like the ones that create our earthly weather. This is a thermodynamic chasm. The dayside is an oven, constantly baking under the star's rays, while the nightside is a cryogenic freezer, radiating all its heat into the void of space. This creates a colossal imbalance in atmospheric pressure. the intensely heated air over the dayside ocean expands and rises, creating a permanent zone of low pressure. Meanwhile, on the night side, the air is frigid, dense, and constantly sinking, creating a massive, stable zone of high pressure. Nature abhors such an imbalance, and the atmosphere responds with a breathtakingly simple and powerful solution. It moves. Air rushes from the high-pressure night side toward the low-pressure day side in a relentless, planet-encircling river of wind. But without a rotating planet to deflect these winds into familiar cyclonic patterns, as the Coriolis effect does on Earth, they would travel in a much more direct path. The result would be supersonic winds screaming across the terminator line from the dark side to the light side, traveling at speeds that could easily exceed 1,000 kilometers per hour. These wouldn't be gusts or storms, they would be a permanent, atmospheric feature as fundamental to this world as its oceans of ice and water. As these frigid gales blast onto the dayside, they encounter the superheated, moisture-saturated air rising from the warm ocean. The collision is instantaneous and violent. The cold air slams into the warm, moist air, forcing it to rise at an incredible rate. This rapid ascent causes the water vapor to condense out with explosive force, generating storms of unimaginable power and scale. You wouldn't have individual thunderstorms popping up and dissipating. You'd have a permanent, planet-wide band of convective fury right where the cold meets the hot. This constant, violent uplift of warm, wet air over the dayside ocean can coalesce into one of the most dramatic weather phenomena imaginable. A permanent superhurricane or megastorm locked directly over the substellar point. Picture a hurricane the size of a continent, but one that never, ever moves. It doesn't spin away and weaken over land because there is no land to cross. It just sits there, anchored by the star's heat below and fed by the endless supply of moisture evaporating from the ocean. Its eye wall would be a terrifying, permanent structure of towering thunderclouds, with rainfall measured in meters per hour, an eternal deluge falling back into the warm sea that fuels it. The energy contained within this single weather system would dwarf the total energy consumption of our entire human civilization for millennia. It would be the dominant feature of the dayside, a swirling, chaotic heart in the center of an already dynamic ocean, constantly redistributing heat and acting as a powerful engine for the planet's global circulation. Yet the atmosphere's work doesn't end there. All that rising air on the dayside has to go somewhere. It can't just pile up at the top of the atmosphere. So it flows high up in the upper atmosphere, back toward the cold night side to complete the cycle. As this air travels across the planet's roof, it cools, and by the time it reaches the night side, it's frigid and dense. It then sinks back down over the dark hemisphere, completing the atmospheric conveyor belt. This simple, global circulation, low-level winds flowing from night to day, and high-level winds flowing from day to night, is the primary mechanism by which the planet struggles to balance its immense thermal inequality. It's a constant, heroic, but ultimately losing battle as the star's energy endlessly pours onto one side and space's vacuum endlessly cools the other. This grand cycle also has a profound effect on the terminator line, that narrow strip of perpetual twilight. As the high-altitude air flowing from the dayside cools and sinks over the night side, a portion of it descends right along the terminator itself. This creates a zone of relative atmospheric stability, a calm buffer sandwiched between the raging winds. This is where something truly magical happens with the planet's water. The warm, moisture-laden winds from the dayside, as they are forced upward by the incoming cold air, dump a significant portion of their water as rain or snow right along this boundary. The terminator line could be a place of permanent, gentle precipitation, a silent, endless fall of snow, or a steady, misty rain, depending on the exact local temperature. This constant delivery of water from the atmosphere, frozen or liquid, would be a crucial source of hydration for any potential landmasses or icy coasts in the twilight zone. It would feed the glaciers, top up the meltwater lakes, and provide a direct atmospheric conveyor belt of a key ingredient for life from the warm ocean to the habitable rim. The climate of an eyeball Earth, therefore, is not just a destructive force of supersonic winds and megastorms. It is also a delicate, planet-wide water distribution system, painting the terminator in shades of frost and mist and quietly nurturing the very environments where life could take its first tentative steps. To understand why the galaxy might be teeming with these strange staring worlds, we need to turn our gaze to the most common type of star in the cosmos, the red dwarf. These faint, cool embers make up an estimated 70 to 80% of all stars in the Milky Way, meaning they are the default stellar neighborhood. Their prevalence alone makes them statistically the most likely place to find planets, but it's their specific characteristics that make them the perfect, and perhaps only, nurseries for eyeball Earths. The first and most critical factor is their sheer longevity. Unlike our Sun, which will burn for a total of about 10 billion years, a typical red dwarf has a truly astronomical lifespan measured in trillions of years. They burn their nuclear fuel with a slow, steady frugality that makes them virtual fixtures of the cosmos. This longevity offers an unimaginably long, stable window for the slow, delicate processes of planetary formation, the establishment of stable climates, and the gradual, patient evolution of life. A civilization arising around a red dwarf could potentially look forward to a future that stretches across eons, a continuity of existence our own sun-worshipping species can scarcely comprehend. However, this stability comes with a significant trade-off: their faintness. A typical red dwarf emits only a tiny fraction of the light and heat of our Sun. For a planet to receive enough warmth for liquid water to exist on its surface, to reside in the habitable zone, it must orbit extraordinarily close to its dim parent star. We're talking about distances that are a mere fraction of Mercury's orbit around our Sun. A year on such a planet might last only 10 to 20 Earth days. It is this intimate proximity that seals the planet's fate. At such close range, the star's gravitational pull is immensely powerful, and it's this force that orchestrates the tidal locking we discussed earlier. The process becomes not a remote possibility, but a fundamental and unavoidable outcome of orbital mechanics. Every single planet orbiting within the liquid water habitable zone of a typical red dwarf is almost certainly tidally locked, presenting one face permanently to its sun. This simple, inescapable fact of physics means that the vast majority of potentially habitable real estate in our galaxy likely exists as worlds of permanent day and permanent night. The search for an Earth twins a world with a 24-hour day and a global climate might be a search for a cosmic rarity, while the true champions of habitability are these bizarre, eyeball-shaped planets. This stands in stark contrast to the possibility of an eyeball Earth forming around a star like our own Sun. For a planet to be tidally locked to a G-type star like ours, it would have to orbit so close that its surface would be scorched into a molten wasteland, far too hot for any liquid water or life as we know it. Our Sun's habitable zone is located much farther out, in a region where its gravitational influence is simply not strong enough to induce synchronous rotation within the lifetime of the universe. A planet like Earth, orbiting at our distance, experiences a much weaker tidal force, allowing it to retain its rapid spin for billions of years. This is why, in our own solar system, we see no true eyeball Earth. The only objects that are tidally locked to the Sun, like Mercury with its complex resonance, are either hellishly hot or frigidly cold, with no temperate twilight zone to speak of. This makes our own vibrant, rotating Earth the true oddball in the grand scheme of things, while the silent, staring faces of tidally locked worlds are likely the galactic norm for habitable planets. But the relationship between a red dwarf and its close orbiting planet is not without its perils, and this brings us to a critical factor that could make or break the habitability of these worlds: stellar activity. Young red dwarfs are notoriously tempestuous. They are prone to violent, frequent flares that can suddenly and dramatically increase their brightness by hundreds of times in just a few minutes, bathing any nearby planets in intense bursts of ultraviolet and X-ray radiation. For a planet tidally locked and orbiting so close there is no escape, the entire dayside hemisphere would be subjected to this sterilizing fury, which could easily strip away a young planet's atmosphere and boil off its oceans. Furthermore, many red dwarfs are also racked by powerful coronal mass ejections, colossal eruptions of stellar plasma that could directly bombard the planet's atmosphere, eroding it over time. A planet's ability to survive its star's tumultuous youth and hold onto a protective atmosphere is the first and greatest challenge it must overcome to ever have a chance at developing an eyeball Earth climate. This means that while red dwarfs create the necessary conditions for tidal locking, they also pose an existential threat that could prevent most of their planets from ever becoming habitable oases, winnowing down the number of potential eyeball Earths significantly. Science fiction has long served as a prophetic playground for the human mind, offering a canvas where writers and filmmakers can paint visions of worlds that push the boundaries of physics and biology. Long before the term eyeball Earth entered the scientific lexicon, authors were imagining the profound psychological and physical reality of living on a planet with a fixed star. One of the most iconic and early examples comes from Isaac Asimov's 1957 novel The Naked Sun, which depicts the planet Solaria. This world orbits its star in a synchronized lock, creating a society where human inhabitants live in isolated splendor on the dayside, developing a deep, pathological fear of direct personal contact while relying on robotic servants for all their needs. The permanent, unending daylight fundamentally shapes their entire culture, their architecture, and even their concept of privacy, presenting a fascinating exploration of how environment can dictate social evolution. Asimov's vision brilliantly anticipated the idea that the physical conditions of a tidally locked world would inevitably forge a civilization unlike any we could recognize. Decades later, film and television brought these stark landscapes to life with stunning visual clarity. The movie Pitch Black presents a powerful, if terrifying, depiction of such a world. The desolate desert planet is besieged by a relentless sun, its human visitors stranded under a scorching sky with 3 suns. While not a perfect one-to-one example of tidal locking, the film's central horror, the arrival of an eclipse that plunges the world into a periodic darkness, awakening lethal, photosensitive creatures from their subterranean shelters, brilliantly plays with the core tension between light and dark that defines an eyeball Earth. It illustrates how even a temporary shift in this delicate balance could unleash existential threats, a dramatic metaphor for the fragility of life in such extreme environments. Similarly, the iconic Twilight Zone episode The Midnight Sun paints a haunting portrait of a world slowly spiraling toward its star, the heat becoming so intense that the very notion of night becomes a distant, cherished memory. The psychological toll on the characters as they face an inescapable, warming doom captures the visceral fear and awe that the concept of a fixed sun can evoke. These fictional portrayals often excel at capturing the sheer, overwhelming scale of the landscapes. Imagine the visual grandeur of a world like Miller's planet from the film Interstellar, a water world orbiting a black hole. While its primary dramatic feature is extreme time dilation due to gravity, its environment a seemingly endless, shallow ocean battered by colossal, periodic waves, echoes the kind of planet-wide oceanic forces that would dominate the dayside of an eyeball Earth. The film's depiction of a world where the horizon is nothing but a continuous, churning sea, with no land in sight and a massive cosmic object permanently fixed in the sky, gives viewers a tangible, breathtaking sense of the sublime and terrifying beauty of such a place. It's a world where the environment itself is the central, antagonistic force, a character in its own right, much as the eternal storm or the endless ice cap would be on a real tidally locked planet. Beyond the spectacle, the best of these stories delve into the nuanced possibilities of life and civilization. Ursula K. Le Guin's masterpiece The Dispossessed features the planet Anars, a barren world that, while not explicitly tidally locked, exists in a fragile ecological balance where human society has been forced to adapt to extreme scarcity. This theme of adaptation is central to the scientific speculation about real eyeball Earths. How would a society develop if all its agriculture and energy production were confined to a single, sun-drenched hemisphere? Would the Terminator line become a coveted, fertile borderland, leading to territorial conflicts between dayside and nightside inhabitants? Or would cooperation be the only path to survival, with the dayside providing solar power and food, and the nightside offering access to deep frozen resources and geothermal energy from beneath the ice? Science fiction allows us to explore these social and ethical dilemmas in a way that raw data cannot, giving a human face to the atmospheric models and orbital mechanics. What is truly remarkable is how often these creative imaginings have paralleled, and in some cases even predicted, the theories now being developed in scientific papers. The concept of a habitable terminator line, a band of perpetual twilight where temperatures might be moderate enough for liquid water, is a mainstay of modern astrobiology. Yet, it was a concept visually realized decades ago in art and film. The idea of a subsurface ocean on the frozen nightside, warmed by geothermal vents and potentially hosting an entire ecosystem independent of sunlight, is a plot point straight out of Arthur C. Clarke's Chinese letter, Odyssey 2, and its depiction of Europa, a concept that has since moved from pure fiction into a leading hypothesis in our search for life. These narratives have done more than just entertain. They have educated and inspired. They have prepared the public imagination for the incredible discoveries that might be just over the horizon, allowing us to greet the news of a real eyeball Earth discovery not with confusion, but with a sense of thrilling recognition, as if we are encountering a world we have visited in our dreams all along. Turning from the realm of imagination and theory to the tangible frontier of modern astronomy, the quest to find actual eyeball Earths is underway, a sophisticated treasure hunt conducted with some of humanity's most advanced instruments. The first crucial step in this search is simply finding these distant worlds, a task that relies on a technique as elegant as it is effective, the transit method. Imagine a distant red dwarf star, a faint pinprick of light in the vast ocean of space. As a planet orbits this star, there's a chance its path will carry it directly between the star and our telescopes here on Earth. When this alignment happens, the planet blocks a tiny, almost imperceptible fraction of the star's light, causing a minuscule periodic dimming. For a planet in the tight habitable zone of a red dwarf, this dip in brightness is repeatable and regular, happening with the precise clockwork of its short orbital period, perhaps every 10 or 20 days. This is the primary method used by planet hunting missions like Kepler and TESS, the transiting exoplanet survey satellite. Kepler, by staring fixedly at one patch of the sky, revealed thousands of worlds, teaching us that planets are common. Its successor, TESS, now conducts a panoramic survey of almost the entire sky, specifically targeting the brightest nearby red dwarfs, the very stars most likely to host these tidally locked planets. It is through these meticulous observations that we first identify the candidates, the dots of light that periodically wink, suggesting a world might be there. But confirming a planet's existence is only the beginning. The next and far more challenging step is to characterize its environment, to determine if it has an atmosphere and what that atmosphere is made of. This is where the transit method reveals its true power. When a planet transits its star, a small amount of starlight filters not past the planet, but through the very rim of its atmosphere if one exists. The gases in this atmospheric shell will absorb specific wavelengths of this stellar light, leaving behind a unique chemical fingerprint in the starlight that finally reaches our telescopes. By splitting this light into a spectrum, a rainbow of colors, astronomers can read these fingerprints, identifying the telltale signatures of various molecules. They are searching for the key ingredients that would make an eyeball Earth not just a barren rock but a living world. The most fundamental of these is water vapor. Detecting a strong, persistent signal of water vapor in the atmosphere of a tidally locked planet would be a monumental discovery. It would confirm that the planet has the essential solvent for life and, given the extreme temperature differences, strongly suggest the presence of that vast, warm dayside ocean and a frozen nightside, the very definition of an eyeball Earth climate. The hunt, however, goes far beyond just water. Scientists are also on the lookout for so-called biosignatures, gases that are readily produced by living processes and are difficult to maintain in an atmosphere through geology alone. The most famous of these is molecular oxygen, or O2. On Earth, our oxygen-rich atmosphere is almost entirely a product of photosynthesis, a relentless biological process that would be supercharged on the permanent dayside of an eyeball Earth. If astronomers were to detect significant oxygen in the atmosphere of such a planet, alongside water vapor, it would be the most compelling hint yet that life may have found a way there. Yet, interpretation is key. Oxygen can, in some rare circumstances, be produced abiotically, such as when intense ultraviolet light from a star splits apart water molecules in the upper atmosphere. This is why context is everything. Researchers would also look for other gases that often accompany life, such as methane. Seeing both oxygen and methane together in an atmosphere is particularly exciting, as these gases readily react with one another and would quickly disappear unless they were being continuously replenished, potentially by a thriving biosphere. This is the extraordinary promise of the James Webb Space Telescope, or JWST. With its massive gold-coated mirror and suite of incredibly sensitive infrared instruments, Webb is uniquely equipped to perform this delicate atmospheric interrogation. Its first targets are the small, rocky planets orbiting the calmest nearby red dwarfs, like those in the TRAPPIST-1 system, a compact solar system with several Earth-sized worlds sitting squarely in the habitable zone. For a suspected eyeball Earth, JWST observations could be revolutionary. It could measure the temperature difference between the dayside and nightside directly, confirming the planet is tidally locked. It could analyze the atmospheric composition at different points in the planet's orbit, potentially even mapping the distribution of clouds and weather patterns. A detection of water vapor with hints of oxygen and a climate model that points to a warm ocean and a cold ice cap would transform a candidate from a data point into a destination, a world that embodies the stunning and beautiful extremes of planetary formation and the enduring, adaptable power of life. Of all the potential eyeball Earths we've theorized, none captivates our imagination quite like the one that is, cosmically speaking, right next door. Nestled in the habitable zone of Proxima Centauri, the closest star to our own Sun at just over 4 light-years away, orbits a rocky world known as Proxima Centauri b. This isn't a distant, abstract possibility. It's a tangible destination, a world that could be the first we ever visit with robotic probes, and the one that most starkly presents the paradox of these synchronously locked planets. The very factors that make it so compelling, its proximity and its location in the habitable zone of a red dwarf, also place it in the center of a vigorous scientific debate about the true nature of its environment and its potential to host an ocean or even life. The discovery of Proxima b was a landmark moment in astronomy, but its parent star presents a host of formidable challenges. Proxima Centauri is a flare star, prone to sudden, violent eruptions that can unleash torrents of ultraviolet and X-ray radiation. For a planet orbiting as close as Proxima b does, with a year lasting a mere 11 Earth days, these stellar tantrums are not a minor inconvenience, they are existential threats. Early in the planet's history, such intense flaring could have stripped away a thick primordial atmosphere and boiled off any global ocean it might have originally possessed. This is the primary argument for a pessimistic view of the planet's habitability, that it may be a barren, irradiated rock, its surface scoured clean by eons of stellar fury, a cautionary tale about the harsh realities of life orbiting a red dwarf. The relentless particle flux from these flares could have slowly eroded any protective magnetic field, leaving the planet's surface exposed and uninhabitable. Yet, nature is remarkably resilient and alternative, more hopeful scenarios abound. It is entirely possible that Proxima b formed with a massive enough reservoir of water, far more than Earth's oceans, that even significant atmospheric loss and evaporation couldn't completely eradicate it. In this more optimistic model, the planet could have weathered its star's violent youth and settled into a stable, eyeball Earth configuration. The intense heat on the dayside would maintain a vast, warm ocean, while the deep cold of the nightside would preserve a colossal ice cap. The planet's atmosphere, though perhaps thinner than Earth's, could be robust enough to facilitate the global heat and moisture circulation we discussed, creating a temperate band along the terminator line. Furthermore, some models suggest that Proxima b could possess a powerful magnetic field, generated by a still molten core, which would act as a vital shield, deflecting the star's most damaging radiation and protecting any tenuous atmosphere that remains. The presence of such a magnetic shield would dramatically increase the chances that Proxima b is a living world, not a dead one. This central question, does Proxima b have surface water, is what future observations are desperate to answer, and the planet's tidal locking gives us a unique observational advantage. Because one side is permanently facing us while the other is forever hidden, we can attempt to measure the thermal emissions from both hemispheres. Advanced telescopes like the James Webb Space Telescope could potentially detect the infrared signature of the planet. If Proxima b is a classic eyeball Earth, the data would reveal a stark temperature contrast, a relatively warm, bright spot on the dayside hemisphere corresponding to the open ocean, and a profoundly cold, dark signal from the icy nightside. Such a detection would be the most direct evidence yet for this exotic planetary state. Even more telling would be spectroscopic data gathered during a transit. As starlight filters through the atmosphere on the dayside limb, it could reveal the chemical fingerprints of water vapor, methane, or even oxygen. A strong water vapor signal, combined with the thermal map of an eyeball, would paint a compelling picture of a world with a dynamic, liquid water cycle. The implications of confirming an eyeball Earth so close to home would be nothing short of revolutionary. It would transform Proxima Centauri b from a subject of theoretical debate into a primary target for the next generation of interstellar exploration. Initiatives like Breakthrough Starshot, which aims to send lightweight, laser-propelled nanoprobes on a flyby mission to the Proxima system, suddenly have a clear and astounding objective: to capture the first ever close-up image of an alien Earth. Imagine one of these tiny craft, after a decades-long journey, turning its camera back towards the planet as it speeds past. The image that streams back to Earth would show a breathtaking celestial marble, a world split in half. One side a brilliant, swirling blue of a sun-drenched ocean, the other a stark, featureless white of eternal ice, separated by a thin, hazy line of perpetual twilight. It would be a view that fundamentally alters our place in the cosmos, proving that worlds of stunning beauty and potential are not just out there in the abstract, but are waiting in our immediate neighborhood, challenging us to reach out and discover what or who might be gazing back from that narrow band between the light and the dark. So how do we move from these captivating theories to concrete predictions about the climate and habitability of worlds light years away? We can't send a probe to take a temperature reading, so instead, scientists turn to a powerful digital crystal ball, sophisticated global climate models. These are not simple simulations. They are immensely complex computer programs that attempt to replicate the entire fluid dynamics of a planet, from the churn of its deepest oceans to the flow of its upper atmosphere. To model an eyeball Earth, researchers start by building a virtual planet from the ground up, feeding in a set of initial conditions that would make any video game designer envious. They define the planet's gravity, its axial tilt, which for a tidally locked world is often negligible, and the precise characteristics of its star, including the spectrum and intensity of radiation it emits. Then comes the real magic. They program in the fundamental laws of physics, the laws of thermodynamics, fluid motion, and radiative transfer, and set the digital clock ticking to see how this complex system evolves over centuries or millennia. A critical variable in this digital experiment is the composition and thickness of the atmosphere. Is it a thin, wispy envelope of nitrogen like Mars, or a crushing, dense shroud of carbon dioxide like Venus? Or perhaps like Earth, it's a robust mix of nitrogen and oxygen with trace amounts of potent greenhouse gases like water vapor and carbon dioxide. Each scenario paints a dramatically different picture of the planet's future. A dense atmosphere with strong greenhouse gases is incredibly effective at trapping heat. On the dayside of an eyeball Earth, this would prevent the star's energy from simply bouncing back into space, helping to maintain that vast, warm ocean. More importantly, a thick atmosphere is a powerful heat transporter. It can efficiently carry warmth from the dayside deep into the nightside, significantly raising the temperatures in the eternal dark and preventing the entire atmosphere from freezing solid. A planet with a thin atmosphere, by contrast, would have a much more extreme climate. The dayside would be scorching hot, but with little atmospheric capacity to move that heat. The nightside would plunge to lethally cold temperatures, creating a world of two absolute extremes with a much narrower, less habitable terminator zone. Another make-or-break factor is the presence and depth of a global ocean. Water is the great climate moderator. Its high heat capacity means it can absorb colossal amounts of solar energy without a drastic rise in temperature, and its ability to flow allows it to distribute that heat around the planet. In these models, scientists can tweak the ocean depth to see how it affects the climate. A deep, planet-wide ocean acts as a massive thermal battery. It absorbs the relentless stellar radiation on the dayside, and through the powerful currents we discussed, it moves that stored thermal energy around, significantly warming the nightside and broadening the temperate area of the terminator line. A shallow sea or a world with scattered lakes, however, would have a much weaker stabilizing effect. The dayside land would heat up intensely, creating a searing desert, while the nightside would become impossibly cold. The result would be a planet with a much more hostile environment, where the sweet spot for liquid water is reduced to a razor-thin line. The models show that a deep ocean isn't just a nice feature for an eyeball Earth. It's likely a prerequisite for achieving any kind of global habitability. The output of these millions of lines of code is a dynamic, full-color map of the entire planet, forecasting everything from surface temperatures and wind speeds to precipitation patterns and sea ice coverage. The most robust simulations consistently reveal a fascinating triple-zone world. They confirm the existence of a hot, stable point directly under the star, often home to that permanent superstorm. They show the expansive, deep freeze ice cap on the nightside, and most importantly, they highlight the critical importance of the terminator line. The models predict that under a wide range of atmospheric and oceanic conditions, this twilight band can maintain temperatures remarkably friendly to liquid water. It's not a fantasy, it's a persistent, stable feature emerging from the physics. This is where the search for life gains its scientific footing. By running countless simulations, climatologists can identify which combinations of atmospheric pressure, greenhouse gas levels, and ocean depth produce a broad, stable terminator region. This allows us to refine our search, prioritizing real exoplanets that match these most promising digital templates, bringing us one step closer to finding a world that doesn't just look like an eyeball, but one that truly has the potential to see life blossom in its eternal twilight. This brings us to one of the most pivotal and unresolved questions in planetary science. When a water-rich world becomes tidally locked, what is its ultimate destiny? Does it become the eyeball Earth we've been envisioning, with a liquid ocean iris staring out at its star, or does it succumb entirely to the cold, transforming into a global ice rink, a snowball Earth? This isn't just academic trivia, it's a fundamental debate about climatic tipping points and the delicate forces that determine whether a world becomes a potential haven for life or a permanently frozen vault. The outcome hinges on a fragile battle between two powerful opposing feedback loops, and the balance is so fine that a small nudge in either direction can seal a planet's fate for billions of years. On one side of this cosmic tug-of-war is the ice albedo effect, a powerful positive feedback loop that can plunge a planet into a deep freeze. Albedo is simply a measure of how much light a surface reflects. Fresh snow and ice have a very high albedo, meaning they reflect most of the sunlight that hits them back into space. Now, imagine a tidally locked planet where ice begins to form on the night side. As that ice sheet grows, it reflects more and more of the star's energy away, preventing the planet from absorbing heat. This causes the global temperature to drop, which allows the ice to expand even further into the terminator zone and toward the dayside. As the ice advances, the albedo increases further, reflecting even more energy and driving temperatures down even more. This is a runaway feedback loop, a climatic avalanche that, if left unchecked, could theoretically encase the entire planet in ice from the night side all the way across the dayside, creating a global snowball. In this state, the planet's bright, white surface would act like a giant mirror, making it incredibly difficult for the star's feeble warmth to ever melt its way back in. But standing against this frigid takeover is another powerful force, the greenhouse effect, a planet's built-in heating system. For a world orbiting a red dwarf, this isn't a luxury, it's a necessity for survival. A substantial atmosphere containing greenhouse gases like water vapor, carbon dioxide, or methane acts as an insulating blanket. It allows visible light from the star to pass through and warm the surface, but it traps the infrared heat radiation that the planet tries to emit back into space. On the dayside of a tidally locked planet, this trapped heat is the only thing preventing the ocean from constantly boiling away, but its more crucial role is in fighting the ice. A strong greenhouse effect keeps the temperature at the substellar point high enough to maintain that patch of open ocean. This liquid water, in turn, has a very low albedo. It absorbs most of the stellar energy that hits it, converting it into heat that fuels the ocean currents and atmospheric circulation that pump warmth toward the night side. This creates a stabilizing negative feedback loop. The open ocean absorbs heat, which helps maintain the greenhouse effect, which prevents the ice from advancing, which keeps the ocean open. The ultimate fate of the planet depends on which of these two competing forces wins this relentless battle. The key threshold is whether the star's energy at the substellar point is intense enough to create a zone of melting that can resist the encroaching ice from the night side. If the star is too dim or the planet's atmosphere is too thin, the ice albedo effect will run away and the world will become a snowball. If the star provides just enough warmth and the greenhouse blanket is thick enough, the melting will hold the ice at bay, resulting in a stable eyeball Earth. There's even a third, more exotic possibility, a jellyfish Earth where the heat transport is so efficient that the ocean doesn't just form a circular patch, but instead extends in a long, trailing tail away from the substellar point, like the tentacles of a jellyfish, as warm water is pulled far into the night side by powerful currents. This illustrates just how dynamic and sensitive these climates can be. Scientists use their most advanced climate models to simulate this epic struggle, and the results show that the difference between a frozen ball and a habitable eyeball can come down to surprisingly small changes. A slight increase in atmospheric carbon dioxide, a marginally more luminous star, or a deeper ocean that can store more heat can be all that stands between a sterile ice world and one with a vast, life-giving sea. This makes the search for eyeball Earths not just a search for planets, but a search for planets that have successfully navigated this climatic tightrope, worlds that have achieved a perfect and perhaps precarious balance between fire and ice. The prospect of life on an eyeball Earth forces us to completely reimagine biology's playbook, pushing the boundaries of what we consider a habitable environment into realms of stunning extremity. Beginning with the dayside ocean, we find a world supercharged with energy, a place where the concept of night does not exist to interrupt the constant driving force of photosynthesis. Here, the most fundamental life forms would not be simple, free-floating algae as we know them. Instead, they would likely evolve into vast, cohesive structures, planets spanning mats or sprawling, floating continents of vegetation. These would not be passive carpets, they would be dynamic, complex ecosystems in their own right. To handle the perpetual, high-intensity light, these organisms would develop sophisticated biological sunscreens, perhaps with deep black or violet pigments tuned to absorb a broader spectrum of radiation while protecting their delicate internal machinery. They might form buoyant, leathery sheets that cover millions of square kilometers, their undersides teeming with symbiotic organisms that feed on the organic material they shed. These megamats could even influence the planet's climate by altering the ocean's albedo, their dark surfaces absorbing more heat and further stabilizing the warm basin of the dayside sea. Predators in this sun-drenched world might not hunt by sight alone, but by sensing the subtle chemical trails or electrical fields generated by the mats, navigating a three-dimensional world where the only darkness is found in the deep, cold currents flowing in from the terminator. Beneath the sunlit surface, at the very bottom of the dayside ocean, life could follow an entirely different and completely independent path. Here, in the abyssal plains and trench systems, no glimmer of sunlight ever penetrates. The energy for life would come from within the planet itself, from the slow, steady heat and chemistry seeping through the seafloor. Hydrothermal vents, similar to the black smokers and lost cities of Earth's mid-ocean ridges, would act as oases in the deep dark. These geological features would spew superheated, mineral-rich water into the cold depths, supporting lush communities of organisms that thrive on chemosynthesis. Instead of using sunlight, these microbes would harness the chemical energy from hydrogen sulfide, methane, or hydrogen, converting it into organic matter. This would form the base of a food web that could include towering, silicon-based tube worms, blind, pale shrimp with exquisite sensitivity to vibration, and strange, armored crabs scuttling across mineral formations that glow with their own ethereal geothermal light. This entire ecosystem would be utterly cut off from the world above, a hidden civilization of the deep that might evolve for millions of years completely unaware that their planet has a surface bathed in eternal, brilliant light. Venturing into the permanent twilight of the Terminator line, we encounter what may be the most complex and fascinating of all the potential biospheres. Life here exists on a knife's edge, literally and figuratively, balanced between the blazing energy of the dayside and the frozen silence of the nightside. Photosynthesis is still possible, but it becomes a game of supreme efficiency. Plant life would be adapted to capture every precious photon of the low-angle, reddish light, likely evolving leaves in deep shades of black or ultra-dark red to maximize absorption. We might find vast, sprawling forests not of trees, but of massive, fungal-like organisms or incredibly dense, low-lying mosses and lichens that cling to rocky outcrops and the icy shores. For animal life, the Terminator would create a world of starkly defined microclimates. A creature could regulate its body temperature simply by moving a few hundred meters, toward the dayside to warm up or toward the nightside to cool down. This would lead to highly specialized migratory patterns, with entire herds or flocks undertaking daily vertical journeys up mountain slopes or horizontal treks across the band to maintain their ideal temperature. Communication in this dim world might rely less on vision and more on sound, smell, or even bioluminescence. Imagine the nightside edge of the Terminator, where the only light comes from the starry sky and the faint greenish glow of countless organisms illuminating the frozen landscape, creating a world of living constellations. The greatest biological enigma, however, lies on the nightside, buried deep beneath the global ice cap. In the subsurface ocean warmed by geothermal heat, life would face its ultimate test: total darkness, immense pressure, and complete isolation. A biosphere here would be a relic, a snapshot of life that might have originated in the dayside ocean and was trapped eons ago. Or it could be a Genesis story all its own, born from the chemistry of hydrothermal vents on the seafloor. In either case, evolution in this environment would take a dramatic turn. With no light at all, organisms would lose their eyes entirely, instead developing exquisite sensitivity to subtle changes in water pressure, electrical fields, or minute vibrations. The base of the food web would be chemosynthetic bacteria, much like in the deep dayside, but the predators here could become giants of the abyss. In the absence of a day-night cycle and with a stable, energy-efficient environment, life could grow to enormous sizes, with filter feeders the size of whales drifting through the dark waters, feeding on clouds of microbes, and predatory squid-like creatures with razor-sharp beaks hunting in the perpetual silence. The lack of seasons or any external timekeeping mechanism could lead to extraordinarily long lifespans, with organisms living for thousands of years, their metabolism slowed to match the steady, unhurried pulse of their geothermal world. This leads to a profound and captivating question: could life from one hemisphere ever interact with life from another? Could there be any biological exchange across the formidable barriers of the eyeball Earth? The deep ocean currents that slowly circulate between the dayside and nightside could act as a kind of planetary bloodstream, carrying microbial life, spores, or dormant eggs from one extreme environment to the other. A hardy microbe from the warm surface waters of the dayside, frozen into a piece of ice that calves from the Terminator, could be carried by deep currents into the nightside subsurface ocean, seeding that isolated world with new genetic material after a journey of millennia. Conversely, chemosynthetic life from the deep nightside vents, adapted to total darkness and high pressure, might occasionally be thrust up into the dayside abyss through volcanic activity, presenting a completely alien form of life to the sun-dependent ecosystems above. While complex, intelligent life would likely be confined to the specific hemisphere it evolved in, the planet itself serves as a grand, if slow, mixer of biological potential, ensuring that even the most isolated environments are not entirely cut off from the creative, relentless force of evolution. The life of an eyeball Earth, therefore, would not be a single story, but a collection of interconnected yet distinct biological sagas, each adapted to its own unique realm of light, dark, and twilight, showcasing the incredible versatility and tenacity of life in the cosmos. One of the most fundamental questions about life on an eyeball Earth is how it would power itself, and this forces a radical rethinking of photosynthesis, the very process that underpins most ecosystems on our own planet. Here, on a world without sunsets, the primary challenge isn't a lack of light, but an overwhelming, unending surplus of it. Constant, high-intensity radiation presents a dual threat. It can damage the delicate molecular machinery of photosynthesis through a process called photoinhibition, and it creates immense oxidative stress. On Earth, plants use the regular cycle of night to repair this cellular damage. In a star-fixed ocean, that crucial recovery period simply doesn't exist. Life here couldn't rely on the familiar rhythms of day and night. Instead, it would need to evolve sophisticated, built-in repair mechanisms that operate continuously, even as the organism is actively converting sunlight into energy. This would require a biochemical toolkit far more advanced than anything we see in terrestrial plants, likely involving multiple redundant systems and powerful antioxidants working around the clock to prevent a catastrophic cellular meltdown under the eternal glare. The organisms that conquer this sun-drenched hemisphere would probably not look anything like the discrete plants or algae we're familiar with. A far more likely scenario is the rise of vast, cohesive superorganisms, gigantic, floating mats of photosynthetic life that could span entire continents of ocean. These wouldn't be passive, simple scums. They would be complex, multi-layered ecosystems in their own right. Their structure would be key to their survival. The top layer might consist of cells packed with protective pigments, appearing deep black or violet to absorb a wider spectrum of light while shielding the layers beneath from the most harmful wavelength. Just below, a second layer would house the primary photosynthetic engines tuned to the specific, filtered light that penetrates the canopy. Deeper still, a third layer might contain symbiotic organisms that handle waste processing and nutrient absorption, creating a self-sustaining floating city. These megamats could regulate their buoyancy, perhaps sinking slightly during periods of intense stellar flares or rising to capture more light during comet times, demonstrating a primitive form of behavioral adaptation to their unvarying environment. Yet, not all life on the dayside would be confined to the brilliant surface. As we descend into the depths of the warm ocean, the star's light quickly fades, creating a whole new set of challenges and opportunities for biology. The deep waters of the dayside hemisphere present a twilight zone of their own, a world of permanent gloom sandwiched between the blazing surface and the dark abyss of the seafloor. Here, light is scarce but not entirely absent. Photosynthetic organisms at these depths would become masters of efficiency, evolving to capture the few photons that trickle down. They might grow in sprawling, filamentous networks that maximize their surface area, resembling a dark, underwater moss clinging to rocky outcrops or even the undersides of the floating surface mats. Their pigments would be fine-tuned to the specific blue and green wavelengths that penetrate the deepest, and their metabolism would be incredibly slow, conserving energy in an environment where every single photon is a precious resource. This deep-water photosynthesis would be a fragile, energy-poor existence, but it could support a unique ecosystem of filter feeders and grazers adapted to harvesting this sparse, deep-growing vegetation. For life in the absolute darkness, whether in the deep-sea trenches of the dayside or the entire subsurface ocean of the nightside, the very idea of photosynthesis becomes impossible. In these realms, life must turn inward, drawing energy not from the sun above, but from the planet below. This is the world of chemosynthesis, a process that uses chemical reactions rather than light to produce organic matter. The most promising locations for this are hydrothermal vents, where superheated, mineral-rich water spews from the seafloor. Here, microbes can perform miraculous feats of chemistry, oxidizing hydrogen sulfide, methane, or even hydrogen gas released from the planet's crust to fuel their growth. These chemosynthetic bacteria form the sturdy foundation of an entire food web that operates in total independence from the sun. On an eyeball Earth, these vent systems would be the cosmopolitan cities of the deep, likely more numerous and active than on Earth due to the intense geological forces at play from tidal heating. They would support lush, alien oases in the crushing darkness, with towering tube worms that farm bacteria inside their bodies, blind shrimp with exquisite sensory antennae, and slow-moving, armored snails grazing on microbial lawns. Beyond the dramatic plumes of hydrothermal vents, more subtle chemical energy sources could also sustain life. The constant circulation between the warm dayside and the frigid nightside would create vast gradients of chemicals dissolved in the ocean water. For instance, where oxygen-rich water from the dayside meets anoxic, nutrient-rich water welling up from the depths, a sharp chemical boundary is formed. Microbes could evolve to harness the energy released by reactions across this boundary, essentially breathing different chemicals in a process called redox chemistry. These microbes could form vast, invisible layers in the ocean, or coat the underside of the nightside ice sheet in a thin, living film. This type of metabolism is far less flashy than a towering black smoker, but it could be incredibly widespread, creating a diffuse, planet-wide foundation of chemosynthetic life that fills the water column and sediments, connecting the biospheres of the light and dark hemispheres in a slow, global exchange of energy and matter. The true marvel of an eyeball Earth's biology, therefore, is its stunning diversity of energy sources. A single planet would host a spectrum of metabolic strategies, each perfectly adapted to its specific niche. On the surface, you have hyper-specialized photosynthesizers built for a life of perpetual, intense light. In the deep dayside waters, you find low-light specialists eking out an existence on the faintest glimmers. And in the global dark, from the deep sea vents to the subsurface ocean, you have chemosynthetic communities thriving on the planet's internal heat and chemistry. This isn't a hierarchy with one being superior to the others. It's a testament to life's incredible versatility. Each of these metabolic pathways represents a different solution to the universal problem of survival. And on a tidally locked world, they could all coexist, creating a planetary biosphere of unparalleled complexity and resilience. The life that emerges isn't just adapting to the light or the dark, it's rewriting the fundamental rules of biology, proving that energy for life can be harvested from the star above, the planet below, and the very chemistry of the sea itself. Now, let's contemplate a truly mind-expanding possibility: the rise of intelligent life on an eyeball Earth. Imagine a civilization that has evolved in a world where the sky is not a changing canvas of day and night, but a fixed, predictable dome with a single, unmoving point of light at its very center. This permanent landmark would fundamentally rewire their entire understanding of reality, from their basic philosophy to the very technologies they would invent to master their world. For them, the concept of a moving sun, of a sunrise or sunset, would be a bizarre and alien abstraction, something found only in ancient myth or complex astronomical theory. Their entire sense of direction, their geography, and even their spiritual beliefs would be anchored to the substellar point, the spot directly beneath the star. It would be their true north, their eternal zenith, the absolute center of their known universe. This constant celestial reference point would likely give rise to a culture deeply rooted in stability, predictability, and precise spatial awareness. Their early navigation wouldn't rely on a wandering sun or a spinning star field. It would be incredibly straightforward. To travel toward the light and heat, you would journey inward toward the substellar point. To venture into the cold and dark, you would move outward toward the terminator and beyond. This would create a radial geography, with societies potentially organized in concentric rings around the central, hottest region. The most advanced and populous cities might not be on the coast of a continent, but built on vast, floating platforms in the warm dayside ocean, positioned at the ideal thermal distance from the central point. Their maps would look like dartboards, with the substellar point as the bullseye and the terminator line as the outer ring. This radial worldview could permeate their entire society, from their urban planning and transportation networks to their social hierarchies and even their artistic expressions, creating a culture of centricity that is utterly foreign to our own terrestrial experience. This radically different environment would also forge a unique path for scientific and technological development. For one, their astronomy would face a monumental challenge. They are permanently stuck looking at only one half of the cosmos. The entire nightside hemisphere of the universe is forever hidden from view, a realm of pure speculation. Their first great astronomers wouldn't be looking up at a dark, starry sky. they would be peering through the perpetual, bright haze of their daytime atmosphere, struggling to detect the faint pinpricks of other stars and planets. The very discovery that they are on a planet orbiting a star might come much later in their intellectual history, as the concept of celestial motion is not a daily, observable fact. When they finally did develop spaceflight, their first satellite launches would be revelatory. A probe sent just a short distance into space, turning its camera back toward the planet, would send back the first ever image of their world's dark side, revealing the existence of the colossal ice cap and the thin, glowing band of the terminator, a discovery that would shatter and remake their understanding of their own home. To survive and thrive, an eyeball Earth civilization would need to develop technologies tailored to their extreme environment. On the dayside, the primary challenges are managing the relentless solar energy and navigating the tempestuous planet-wide ocean. They would likely become masters of solar power on a scale we can scarcely imagine, with vast, floating photovoltaic arrays covering millions of square kilometers of the ocean surface. But they would also need sophisticated technology to weather the permanent mega-storm locked over the substellar point. Their seafaring vessels and floating cities would need to be engineered to withstand hurricane-force winds and colossal waves as a constant, normal condition, not a rare emergency. To explore or utilize the night side, they would face the opposite problem, a crippling lack of energy and profound cold. They might develop deep drilling technology to tap into the intense geothermal heat beneath the ice, creating heated, pressurized habitats within the ice sheet itself or on the rocky seafloor of the subsurface ocean. Their version of a polar research station would be a domed city buried under miles of ice, illuminated by artificial light and powered by the planet's own internal fires. The most intriguing technological pursuit, however, would be the mastery of the Terminator line. This narrow, temperate band would be the most valuable and contested real estate on the planet. A civilization advanced enough might attempt grand geoengineering projects to widen this habitable zone. They could deploy gigantic, orbital sunshades to slightly cool the inner edges of the dayside, reducing the intensity of the heat and storms. Conversely, they might attempt to spread dark, heat-absorbing material on the nightside ice cap to slowly melt it back, or build immense pipelines to transport warm water from the dayside ocean into the frozen regions. Their greatest achievement might be the construction of a continuous, planet-girdling city along the entire terminator, a ring of life that leverages the stable temperatures and access to both the liquid and frozen hemispheres. This megastructure would be a testament to a species that has fully embraced the bizarre geometry of its home, turning a line of climatic balance into the backbone of its global civilization. Ultimately, the psychology and philosophy of such a species would be deeply shaped by their cosmic context. They would lack the fundamental metaphors of rebirth and renewal that our cycles of day and night and our seasons provide. Their world is not about cycles, but about permanence and gradient. Their art and literature might be obsessed with themes of balance, duality, and the tension between the static and the dynamic. The concept of the other side, the unseen, frozen hemisphere, could loom large in their mythology, a place of mystery, danger, or spiritual significance. If they were to eventually make contact with a species from a rotating world like Earth, the cultural shock would be profound. We would have to explain the experience of a sunset, the feeling of a cool night breeze after a hot day, and the concept of a sky that constantly changes. In return, they could teach us about a different kind of harmony, one not found in the turning of spheres, but in the delicate, enduring equilibrium between absolute light and absolute darkness. Their very existence would be a powerful reminder that intelligence is not a single path, but a branching tree of possibilities, each shaped by the unique and wondrous constraints of a home world. Looking beyond the theoretical models and the tantalizing hints from spectroscopy, the next great leap in our understanding of eyeball Earths requires us to do something astonishingly direct to see one. For all our advances, every exoplanet image you've likely ever seen is an artist's impression, a beautiful but speculative rendering based on data points and physics. The future of exoplanet science is about to transform that speculation into sight, moving from inferring a world's existence to beholding its actual resolved light. This monumental step is the goal of a new generation of space observatories, instruments designed not just to find planets, but to stare directly at them and capture their portrait. The most ambitious of these projects is NASA's planned Habitable Worlds Observatory, or HWO. Conceived as a flagship mission for the 2030s and beyond, the HWO represents the culmination of decades of technological progress. Its primary, audacious goal is to directly image and characterize at least 25 potentially Earth-like worlds. To achieve this, it will need to be a telescope of unprecedented power and stability, equipped with a coronagraph or a starshade, an external, flower-shaped mask that would fly tens of thousands of kilometers in front of the telescope, perfectly positioned to block the blinding glare of a host star, allowing the faint, reflected light of its orbiting planets to finally shine through. The scientific payoff of such a mission would be nothing short of revolutionary for the study of tidally locked worlds. Consider what the HWO could reveal about a nearby candidate like Proxima Centauri b. Instead of seeing a single pixel of light, advanced processing techniques might resolve that pixel into a distinct, albeit tiny, disk. The first crude images would be a map of brightness and color. And for an eyeball Earth, that map would tell a stunningly clear story. We would see a brilliant bluish-white spot on one hemisphere, the warm, liquid ocean of the dayside reflecting the light of its star. Connected to it, we'd observe a darker, reddish-tinged band encircling the planet, the vegetated or mineral-rich lands of the Terminator line, and covering the rest of the globe, a vast, intensely bright and featureless region would dominate, the highly reflective ice sheet of the permanent nightside. This single image would provide instant visual confirmation of the eyeball Earth hypothesis, moving it from a compelling model to an observed reality. The geography of an alien world, defined by its stark climate, would be laid bare before our eyes for the very first time, but direct imaging is only the beginning. The true power of the HWO lies in its ability to perform detailed spectroscopy on the light it collects from these resolved planets. By analyzing the spectrum of the dayside ocean separately from the Terminator band and the nightside ice, we could move beyond global averages and begin to create a crude but revolutionary weather map of an alien world. From the dayside spectrum, we could measure the precise abundance of water vapor and search for the telltale signatures of chlorophyll or other alien photosynthetic pigments. The Terminator's spectrum might reveal the presence of ozone, a potential biosignature, or show evidence of water clouds and precipitation. The nightside spectrum would largely confirm the presence of various ices, but it might also detect unexpected trace gases, perhaps methane seeping from subsurface sources, hinting at the hidden ocean below. This pointillist approach to planetary science, studying each region in isolation, would allow us to understand the planet not as a single entity, but as a system of interconnected, extreme environments. We could finally test our climate models not against a single data point, but against a full hemisphere's worth of observations, verifying our predictions about atmospheric circulation, heat transport, and the stability of the liquid ocean. The journey to this future, however, is paved with extraordinary engineering challenges. Directly imaging a small, rocky planet is like trying to photograph a firefly hovering next to a massive, brilliant searchlight from thousands of miles away. The star is billions of times brighter than the planet, and the angular separation between them is infinitesimally small. This requires a telescope with a mirror large enough to collect sufficient light and to achieve the necessary resolution, likely exceeding 6 meters in diameter. It also demands a coronagraph or starshade of incredible precision, capable of suppressing the starlight to a level of 1 part in 10 billion. Furthermore, the entire spacecraft must be phenomenally stable, with its optics held to a tolerance smaller than the width of an atom to prevent the faint planetary signal from being washed out by microscopic vibrations. These are not incremental improvements, they are generational leaps in technology. Current missions like the Roman Space Telescope are already testing next-generation coronagraphs that will serve as crucial pathfinders for the HWO, proving the technologies in the harsh environment of space and teaching us how to tease the faintest signals from the cosmic glare. The international scientific community is not standing still while these grand observatories are being designed. A suite of ground-based instruments is also pushing the boundaries of what's possible. The Extremely Large Telescope, or ELT, currently under construction in Chile, will boast a 39-meter primary mirror, making it the world's largest eye on the sky when it sees first light later this decade. While Earth's turbulent atmosphere makes direct imaging of Earth-sized planets incredibly difficult, the ELT, equipped with advanced adaptive optics and powerful spectrographs, will be capable of studying the atmospheres of larger exoplanets in unprecedented detail. It could potentially even attempt to detect the thermal glow from the dayside of nearby tidally locked super-Earths, offering a preview of the kind of data the HWO will provide. These ground-based efforts create a powerful symbiotic relationship with space telescopes. The ELT can perform initial reconnaissance on promising targets, identifying which worlds have atmospheres rich with water or other interesting molecules, thereby providing a priority target list for the more sensitive, dedicated space-based observatories to follow up on with direct imaging. The ultimate dream, of course, is to not just image an eyeball Earth, but to detect unambiguous signs of life on one. The HWO's detailed regional spectroscopy gives us our best shot yet at this holy grail of astrobiology. The mission will specifically search for a combination of biosignatures, the so-called red edge of surface vegetation, the simultaneous presence of oxygen and methane, or the spectral fingerprints of other gases like nitrous oxide that are hard to explain without biology. On an eyeball Earth, the signal might be incredibly strong and localized. Imagine the spectrometer detecting an overwhelming signature of oxygen and a unique pigment absorption feature coming only from the dayside ocean, with a completely different chemical profile emanating from the terminator. This would be powerful evidence that life is not just present, but that it has fundamentally shaped that hemisphere's environment, likely through a form of perpetual, global-scale photosynthesis. Conversely, detecting methane and hydrogen sulfide predominantly on the nightside, coupled with a thermal signature suggesting a subsurface ocean, would point strongly toward a robust chemosynthetic biosphere thriving in the darkness. The ability to pin these potential biosignatures to specific geographic regions on the planet dramatically increases our confidence in interpreting them, helping to rule out the false positives that can plague simpler global measurements. Envisioning the moment when the first resolved image of an eyeball Earth appears on our screens is to imagine a watershed moment for humanity. It would be a discovery on par with the first images of Earth from space, a perspective-shifting revelation that redefines our place in the cosmos. That single picture, a marble of blue, white, and brown, would be tangible proof that worlds of such breathtaking contrast and beauty are not just possible but real. It would tell us that the universe is capable of crafting environments far stranger and more wonderful than we ever dreamed, and that the delicate balance between fire and ice can create stable, long-lived cradles for complexity. The data that follows, the weather maps, the atmospheric compositions, the search for biosignatures would launch a new era of comparative planetology, where we could finally begin to understand the full diversity of habitable worlds. The Habitable Worlds Observatory and its successors are not merely telescopes, they are time machines offering us a glimpse into the future of exoplanet science, a future where the mysterious eyeball Earths transition from fascinating theoretical constructs into known worlds, awaiting our further exploration, and one distant day, perhaps even our visit. But what if we weren't just passive observers of these cosmic eyeballs? What if, in a future thousands of years from now, humanity set its sights on one of these worlds not just for study but for a new home? The idea of terraforming an eyeball Earth represents perhaps the most audacious engineering project conceivable, a deliberate attempt to rewire a planet's entire climate and even its fundamental rotation, forcing it to conform to a rhythm of life born under a moving sun. The primary goal would be to shatter the planet's tidal lock, to set it spinning once more, and in doing so, eliminate the permanent, extreme duality of its hemispheres. The most grandiose proposal to achieve this involves using the solar system itself as a toolkit, specifically by steering a carefully selected stream of asteroids or comets. The concept is as simple in theory as it is complex in execution. You direct these cosmic billiard balls to strike the planet's surface at a precise, grazing angle, each impact transferring a tiny amount of angular momentum. Over centuries, this relentless celestial pummeling would act like a gentle but persistent push on a spinning merry-go-round, gradually nudging the planet into a slow rotation. The challenges, however, are astronomical. The precision required to orchestrate such a sequence of impacts without shattering the planet's crust or boiling away its oceans is beyond our current comprehension. Each impact would be a global extinction-level event, releasing unimaginable energy and potentially undoing any progress by vaporizing the very water and atmosphere you're trying to preserve. The terraforming process would begin with a protracted era of planetary violence, a necessary evil to achieve a distant, peaceful dawn. Faced with the destructive reality of impact-driven spin-up, a more subtle, though equally immense, alternative emerges: the construction of gigantic orbital mirrors known as soletas. This approach accepts the planet's locked state and works within its constraints, aiming not to change the planet's spin, but to change the pattern of light that falls upon it. Envision a fleet of mirrors, each the size of a small continent, positioned at the planet's L1 Lagrange point, the gravitational balance point between the planet and its star. Their purpose would be twofold. The first and most crucial mirror, a vast circular disk, would be stationed not to reflect light onto the dayside, but to cast a permanent, moving shadow upon it. This starshade would orbit in such a way that it creates an artificial day-night cycle for the sun-scorched hemisphere, giving the blazing ocean a period of cooling respite each rotation, and mimicking the conditions that drive weather patterns on Earth. Simultaneously, a second, ring-shaped array of mirrors would be positioned to catch the starlight that would normally miss the planet entirely and redirect it onto the frozen nightside. This gentle, continuous illumination would slowly warm the eternal ice cap, initiating a global melt that would, over millennia, release vast quantities of water vapor and other trapped gases, helping to build a planet-wide atmosphere and raise temperatures from the cryogenic depths. The climatic consequences of such a mirror system would be as profound as they are unpredictable. On the dayside, the introduction of a daily shadow would fundamentally alter the planet's energy engine. The permanent superhurricane locked over the substellar point, deprived of its ceaseless energy source, would likely weaken and begin to break apart into more familiar rotating storm systems. The relentless oceanic currents would slow and reorganize, creating new patterns of heat distribution. The introduction of a cooling period would be a revolutionary event for any potential native life, forcing a dramatic evolutionary shift as organisms that had known only light for billions of years would suddenly have to adapt to a regular period of darkness. On the night side, the slow, patient thaw would be a spectacle of planetary change on the grandest scale. As the miles-thick ice begins to melt, it would reveal a primordial landscape, a rocky crust that has not seen starlight since the planet first formed. New rivers and seas would form, initially freezing over each night, but gradually persisting as the artificial sunlight does its work. The melting ice would also release volatiles frozen within it, gases like carbon dioxide and methane, which would further thicken the atmosphere and accelerate the warming through a runaway greenhouse effect, a dangerous process that would have to be carefully managed to prevent the planet from overheating entirely. Perhaps the most complex challenge would be managing the terminator line, that narrow band of twilight that might already host its own unique ecosystems. As the mirrors redistribute sunlight, this once stable refuge would become a zone of violent transition. The careful thermal balance would be shattered as warm air from the newly cooled dayside clashes with the warming air from the formerly frozen nightside. This could create a belt of immense storms and unpredictable weather, potentially rendering the very region we find most habitable temporarily uninhabitable. The terraformers would face an agonizing ethical dilemma. In our quest to create a world for ourselves, would we be responsible for the potential extinction of an entire native biosphere that had evolved over eons to thrive in the perpetual twilight? The process of planetary engineering becomes not just a technical problem, but a profound philosophical one, forcing us to weigh our own expansion against the intrinsic value of alien life, no matter how strange or primitive it may seem to us. Beyond the mirrors and the impacts, the actual creation of a breathable Earth-like atmosphere would be a millennia-long endeavor in itself. Even after achieving a spin and a more balanced temperature, the planet's air might be thin, toxic, or lack sufficient oxygen. This is where the second phase of terraforming would begin, one that mirrors proposals for Mars. We might seed the new oceans with genetically engineered algae and cyanobacteria, organisms designed to thrive in the specific conditions of this new world and pump out oxygen through photosynthesis on a global scale. We could construct massive automated factories that process the planet's rocks and release trapped gases, or we could redirect comets rich in ammonia and water ice to bombard the planet, deliberately this time to deliver the volatile building blocks of an atmosphere. The entire project would be a multi-generational saga, a testament to human patience and long-term thinking on a scale we have never before attempted. It would require a sustained global or perhaps solar system-wide commitment spanning thousands of years, with each generation maintaining the orbital mirrors, monitoring the atmospheric growth, and guiding the ecological development, all for a payoff they would never live to see. In the end, the dream of terraforming an eyeball Earth holds up a mirror to our own desires and our understanding of what a habitable world should be. It is a vision born from a deep-seated bias for the environment that created us, a world of cycles, of dawns and dusks, of varied climates and seasons. Yet, as we gaze upon the stark, beautiful face of an untamed eyeball Earth, we must ask a difficult question. Are we improving it, or are we simply making it more like us? The monumental engineering, the ethical quandaries, and the sheer timescale involved suggest that such a project may forever remain in the realm of thought experiments. But it serves a vital purpose. It forces us to confront the incredible forces that shape planets and to appreciate the delicate, dynamic balance of our own spinning world. It reminds us that the universe creates habitability in many forms, and that the true future of humanity in the cosmos may not lie in remaking other worlds in Earth's image, but in learning to adapt ourselves to the profound and beautiful strangeness of places like the eyeball Earths, finding our home not by changing the planet, but by changing our own definition of what home can be. Within their starkly divided hemispheres and bizarrely stable climates, these worlds offer us far more than just a spectacle of cosmic extremes. They function as unparalleled natural laboratories, testing our deepest theories about how planets work and where life can take root. The very factors that make them so strange, their permanent dayside and nightside, their planet-spanning temperature gradients, their unique weather patterns, are precisely what make them such powerful tools for science. On Earth, our climate is a fantastically complex tapestry woven from the interplay of rotation, seasons, and a dynamic ocean atmosphere system. it's difficult to isolate individual variables to see how they truly work. But on an eyeball Earth, many of these complications are stripped away. The climate is simplified into a grand global experiment with one dominant variable, an immense and constant difference in heating between one side of the planet and the other. This allows scientists to use these worlds as a crucible for their most advanced climate models, testing predictions about atmospheric flow, heat transport, and ocean circulation in a regime that simply doesn't exist in our own solar system. When a model successfully predicts the supersonic winds or the permanent hurricane on an eyeball Earth's dayside, it doesn't just tell us about that one alien world. It validates the fundamental physics that govern all planetary atmospheres, giving us greater confidence in our understanding of Earth's own past and future climate. This laboratory extends profoundly into the search for life itself, forcing a radical expansion of the very concept of habitability. For decades, the guiding principle has been the habitable zone, the orbital distance where a planet with an Earth-like atmosphere could have liquid water on its surface. But eyeball Earth shatter the assumption that such a planet must also be Earth-like in its rotation. They demonstrate that liquid water, that essential ingredient, can persist in astonishingly narrow and unexpected places, in a hemisphere-wide ocean under a fixed sun, or in a subsurface sea warmed by geothermal vents, or in a thin band of perpetual twilight. By studying these worlds, we are actively rewriting the rules of the game. We are learning that a planet doesn't need a 24-hour day to be alive. It simply needs a stable, long-term source of energy and a way to circulate nutrients. This insight is revolutionizing astrobiology. It means we can no longer dismiss a planet just because it is tidally locked. In fact, given the prevalence of red dwarf stars, we must now consider these extreme worlds as prime candidates in our search. They teach us that life is not a fragile flame that needs perfect Earth-like conditions, but a tenacious force that can exploit energy gradients in ways we are only beginning to imagine, whether from a star that never sets or from the heat of a planet's own core. Perhaps the most profound lesson from these cosmic labs concerns the resilience and evolution of planetary atmospheres. An atmosphere is a planet's lifeline, a protective blanket, and a global transportation network. But on a tidally locked world, this blanket is subjected to a relentless and asymmetric assault. The dayside is baked by constant ultraviolet radiation, which can tear apart water molecules and threaten to strip away lighter gases. The nightside, in deep freeze, acts as a cold trap, potentially causing the entire atmosphere to condense and freeze out onto the surface. The survival of an atmosphere over billions of years on such a world is a testament to the dynamic balance between escape and replenishment. Studying the atmospheres of real eyeball Earth candidates with telescopes like the James Webb Space Telescope allows us to witness this cosmic balancing act in real time. Detecting a thick atmosphere on one of these planets would tell us that powerful geological processes like volcanic outgassing are actively at work, replenishing what is lost to space. It would also suggest that the planet's global winds are efficient enough to transport enough heat to the nightside to prevent a total atmospheric collapse. Each new atmospheric measurement is a data point in a grand experiment about the limits of atmospheric stability, teaching us which kinds of worlds can hold onto their protective shields long enough for life to emerge and flourish. Ultimately, the value of eyeball Earths as cosmic laboratories lies in their power to refine our search strategies for life beyond Earth. They provide a set of concrete, observable predictions that guide where we should point our most powerful telescopes. Instead of looking for a vague Earth twin, we can now search for specific, detectable signatures of these extreme environments. For instance, if a telescope observes an exoplanet that is much hotter on one side than the other, it strongly suggests tidal locking. If the same planet shows a strong signature of water vapor in its atmosphere, the hypothesis of an eyeball Earth configuration becomes incredibly compelling. Furthermore, the unique geography of these worlds means that potential biosignatures might not be evenly distributed. A strong oxygen signal that comes only from the dayside hemisphere could be a powerful indicator of a photosynthetic biosphere operating at a hemispheric scale. Conversely, detecting methane seeping from the nightside could point toward a hidden, chemosynthetic ecosystem in a subsurface ocean. By giving us these specific, location-based clues, eyeball Earths transform the search for life from a shot in the dark into a targeted investigation. They provide a new catalog of what to look for and where to find it, turning the strange, staring faces of these worlds into our most insightful guides in the ultimate quest to discover whether we are alone in the universe. Standing on the surface of an eyeball Earth, the experience would be one of profound and absolute disorientation, a sensory overload that defies every instinct our terrestrial brains have developed over millennia. On one side of you, the landscape stretches out under the unwavering, brilliant glare of a sun that has not moved in a billion years. It hangs fixed at its zenith, a perfect, unblinking eye of fire, casting sharp, unchanging shadows. There is no dawn to anticipate, no high noon to mark the day's peak, and most unnervingly, no sunset to promise a cool evening and a restful night. Time as a cycle tied to the heavens simply does not exist here. The very concept of a day is meaningless. Your entire existence would be governed by geography, not chronology. If you were to walk toward the light, the air would grow thick and heavy with humidity, the ground beneath your feet warming until you reached the shores of that vast, warm ocean, its waves churned by eternal storms. The sound would be a constant, low roar, the voice of a world perpetually in motion under an unending sky. Now turn and look in the opposite direction. The transition is not gradual, it is a stark, breathtaking line. Behind you lies the realm of endless night, a darkness so deep and complete it feels like a physical wall. The temperature plummets and your breath freezes in the air. Looking up, you would see a celestial spectacle denied to all inhabitants of the dayside. A perfect, ink-black sky dusted with countless stars and swirling galaxies, undimmed by any hint of an atmosphere or a rising sun. There are no clouds here, no weather to speak of, just an immense, silent cold that has persisted since the planet's birth. This is not the comforting, familiar darkness of a moonlit night on Earth. This is the absolute black of deep space pressing down on a frozen wilderness. The only light on the ground might be the faint, ghostly luminescence of your own equipment, or the otherworldly shimmer of starlight reflecting off a glacier that is older than entire species on our own world. To stand here is to stand at the edge of the universe, looking out into the infinite void completely alone. But the true heart of this world, the place of most captivating beauty and potential, is the razor's edge you are standing on, the Terminator line itself. This is a world of perpetual golden hour. The sun forever sits exactly on the horizon, a huge, dimmed orb that paints everything in long, deep shadows and a soft, ethereal, reddish light. It is a permanent global sunset, a twilight that will never deepen into night and never brighten into day. The quality of the light would be unlike anything we know. Diffused and gentle, it would erase harsh edges and give the landscape a dreamlike, painterly quality. You could see the stark contrast in a single glance, one horizon ablaze with the colossal, motionless sun, the other a tapestry of the cosmos, with the frozen ice cliffs of the nightside catching the last hints of the warm glow. The silence here would be profound, broken only by the distant crack of ice or the sigh of the wind, a wind that is not a gust but a permanent, river-like flow of air rushing from the frozen dark to the searing light. This experience forces a radical shift in cosmic perspective. We are creatures of a world defined by cycles, the spin that gives us day and night, the orbit that gives us seasons. These rhythms are baked into our biology, our culture, and our very consciousness. On an eyeball Earth, that framework is utterly absent. A civilization born here would have no concept of tomorrow in the way we do. Their mythology would lack stories of a sun god traveling across the sky. Their poetry would have no verses about the dawn's early light, and their science would have taken a completely different path to understanding the cosmos, perhaps focusing first on the mysteries of the deep, star-filled void above their nightside before ever comprehending the nature of their own star. To visit such a place is to understand that our reality is not the default setting of the universe. It is merely one possible configuration in an infinite tapestry of worlds, each with its own rules, its own beauty, and its own unique story to tell. The awe we feel contemplating these worlds is not just about their alien geology. It is a humbling recognition of the sheer creative diversity of the cosmos, and a thrilling hint at the boundless possibilities for life and experience that lie waiting among the stars. This cosmic perspective, where life might flourish in permanent daylight or deep beneath a global ice sheet, brings us face to face with one of the most profound puzzles in science, the Fermi paradox. If the universe is so vast and ancient, and worlds like these are so common, then where is everybody? The prevalence of eyeball Earths offers a compelling and perhaps sobering set of potential answers to this enduring question. It suggests that the very conditions that might make a planet habitable could also erect formidable barriers to the emergence of civilizations capable of building radio telescopes or launching starships. On a tidally locked world, the path from simple life to a technological society may be a much steeper and more treacherous climb than it was here on our gently rotating Earth. Imagine a civilization evolving on the dayside, blessed with boundless solar energy but cursed with a climate of permanent, violent storms. Their entire technological development would be a constant battle against the elements. Building stable structures, developing agriculture, or even achieving basic metallurgy would be infinitely more difficult in a world lashed by supersonic winds and a permanent hurricane. The very foundations of settled society, which on Earth were laid in fertile river valleys with predictable seasons, might never coalesce in such a chaotic and unrelenting environment. Their progress could be perpetually reset by global climatic catastrophes, trapping them in a cycle of advancement and collapse without ever reaching a point where they could look outward to the stars. Conversely, a society arising in the relative calm of the Terminator line would face a different, yet equally daunting, set of constraints. While their climate is stable, their world is geographically narrow, a thin ribbon of habitability wrapped around a globe of extremes. This lack of expansive, diverse landmasses could severely limit the development of complex, competing societies, a driver of innovation and cultural exchange throughout human history. With resources confined to this single band, the impetus for exploration and long-distance trade might be minimal. Why venture into the lethal dayside or the frozen nightside when all you need is contained within a journey of a few hundred miles? Furthermore, the absence of a day-night cycle could fundamentally alter their cognitive development. Our own intelligence is deeply intertwined with patterns, with cycles of activity and rest, with the predictive power of a rising and setting sun. A culture that has never known these rhythms might develop a completely different kind of consciousness, one less focused on linear progress and technological domination, and more on stability, equilibrium, and the immediate local environment. Their greatest intellectual achievements might lie in philosophy or art forms we cannot even conceive, rather than in the engineering required for interstellar communication. Perhaps the most intriguing possibility is that intelligent life does arise on these worlds, but evolves into something so profoundly alien that its very existence is invisible to our current search methods. Our entire search for extraterrestrial intelligence, or SETI, is built on an Earth-centric premise that advanced beings will use technologies we recognize, like radio waves or laser transmissions. But consider a species that evolves in the total darkness of a subsurface ocean. Their entire perception of reality would be based on senses we lack, navigating by sonar, sensing minute changes in water pressure, or communicating through complex patterns of bioluminescent flashes or electrical impulses. Their mathematics and physics might be built around the fluid dynamics of their ocean world and the resonant frequencies of their ice-bound caverns. The concept of an antenna broadcasting into the vacuum of space would be as absurd to them as trying to communicate by modulating the heat of a hydrothermal vent is to us. Their civilization, which could be immensely sophisticated and ancient, would be entirely encapsulated, its achievements and conversations hidden beneath miles of ice, leaving no techno-signature for our telescopes to ever detect. They are not silent, they are speaking a language the universe itself, from our limited vantage point, seems designed to keep secret. This reshapes our understanding of the Great Filter, the hypothetical barrier that prevents life from progressing to a visible galactic stage. Perhaps the filter is not a single dramatic event, but a series of planetary constraints. For a tidally locked world, the first filter is developing a stable, long-term climate that can host liquid water, a challenge many may fail. The next is the emergence of life itself in such extreme conditions. A further filter is the evolution of complex, multicellular organisms without the driving force of pronounced environmental cycles. And the final, most difficult filter may be the leap to a technology capable of interstellar messaging while being confined to a single, climatically fragile band on a world of brutal extremes. It is possible that eyeball Earths are fantastic incubators for life, but terrible crucibles for the kind of intelligence that builds civilizations we can observe from across the galaxy. They may be the universe's most common gardens, teeming with fascinating and complex flora and fauna, but forever lacking the conditions to spawn a gardener who can look up and wonder about the stars. Ultimately, the silent darkness we perceive when we listen to the cosmos may not be a sign of our loneliness, but a testament to the universe's incredible diversity. The Fermi paradox might not have a single answer, but a spectrum of answers tied to the specific environments of the most common habitable worlds. The prevalence of eyeball Earth suggests that our own experience, a technologically noisy species on a temperate, rotating planet, could be the cosmic exception, not the rule. The galaxy might be filled with life, but it is a quiet, hidden, and deeply alien life, adapted to its own unique and permanent realities of light and shadow. Our continued search, therefore, must broaden. We need to look not just for radio signals, but for other, more subtle signs, the chemical fingerprints of massive industrial activity in an exoplanet's atmosphere, or the unnatural thermal glow of a Dyson swarm constructed not around a star, but as a planetary-scale heat source for a civilization on a frozen nightside. The silence is not an emptiness, it is a challenge to our imagination, compelling us to think beyond our own planetary experience and consider the breathtaking possibilities of intelligence shaped by a sun that never moves in the sky. While the classic water-rich eyeball Earth sparks our imagination, the underlying principle of tidal locking can forge worlds of even more extreme and alien character. The same gravitational forces that create a planet with a liquid water iris can sculpt entirely different kinds of staring worlds, depending on the raw materials available during planetary formation. This expands the canvas of possibility from a single, hauntingly beautiful image to a full gallery of cosmic eyeballs, each with its own unique and breathtakingly hostile environment. The first of these exotic variants is the lava eyeball, a vision of a world that has fully embraced the fire of its star. Picture a planet that formed even closer to its red dwarf sun than a water-based eyeball Earth, orbiting so near that the stellar radiation is overwhelming. This world would be perpetually baked, its surface temperatures soaring high enough to melt silicate rock. Just as the ocean on a water world remains liquid only on the dayside, the rock itself would liquefy under the unending glare. The substellar point would become a permanent, seething ocean of molten lava, a vast, glowing cauldron of incandescent rock hundreds of miles across. This would be the planet's brilliant, terrifying iris, a roiling, orange-red pupil of pure magma, constantly churned by unimaginable heat and perhaps even spotted with the cooler, darker spots of semi-solid crustal plates slowly circulating in the molten sea. The rest of the lava eyeball would be a study in the transition from utter fluidity to absolute solidity. Radiating out from this central magma ocean, the temperature would gradually drop. The lava would begin to cool and solidify, first forming a brittle, glassy crust that constantly cracks and remelts, and eventually giving way to a global landscape of barren, solid rock on the nightside. This nightside would be a realm of profound geological silence, a global continent of ancient, frozen basalt, its surface untouched by erosion or weather, preserving meteorite impacts from billions of years ago. The terminator line on such a world would be the most geologically active and unstable region imaginable. It would be a permanent, planet-girdling border war between fire and stone. Here, the solid crust from the nightside is in constant, slow-motion collision with the molten dayside. You would witness colossal lava flows creeping into the darkness, freezing and piling up into immense black obsidian cliffs, while the relentless thermal stress from the dayside causes the nightside rock to fracture and crumble, feeding new material into the magma ocean. The atmosphere on a lava eyeball would likely be thin and composed of vapors outgassed from the molten rock, poisonous soups of sulfur dioxide, sodium, and silicon monoxide, creating a hazy, orange sky that further deepens the hellish landscape. While the chances for life as we know it are virtually zero, the lava eyeball stands as a powerful testament to the creative power of stellar energy, proving that even a world of stone can be sculpted into an eyeball, its gaze a permanent, blazing testament to the power of its sun. On the opposite end of the compositional spectrum lies another fascinating possibility, the Hycean eyeball. This concept builds on a relatively new class of theorized exoplanets called Hycean worlds, planets larger than Earth but smaller than Neptune, with a rocky core surrounded by a massive global ocean and enveloped by a thick, hydrogen-rich atmosphere. Apply the tidal locking principle to such a world, and you get an environment of staggering scale and potential. The dayside of a Hycean eyeball would host a planet-wide ocean, but one far deeper and more vast than on a terrestrial eyeball Earth. This wouldn't be a water ocean sitting on a rocky crust. It could be a water layer dozens or even hundreds of miles deep, potentially sitting atop an exotic form of high-pressure ice with a rocky core far below. The intense, perpetual sunlight would heat the upper layers of this immense sea, but the incredible depth and the global circulation patterns would create a much more complex thermal structure than on a smaller world. The true defining feature of the Hycean eyeball, however, is its atmosphere. Enveloping the entire planet is a deep, dense shroud of hydrogen, a gas that is a powerful greenhouse agent. This atmospheric blanket would be incredibly effective at trapping the star's heat, not just on the day side, but across the entire planet. This has a profound effect on the climate. While a traditional eyeball Earth has a night side cold enough to freeze its atmosphere solid, the strong greenhouse effect of a hydrogen-rich envelope could keep the entire night side of a Hycean world significantly warmer. The temperature difference between the two hemispheres would be less extreme, potentially preventing the formation of a global ice cap. Instead of a stark white sclera, the night side might be a deep, dark blue, a global ocean that remains liquid, albeit much colder, shielded from the vacuum of space by its immense atmospheric coat. The planet might not look like a crisp eyeball from space, but more like a marbled blue marble with a brighter, stormier dayside and a darker, calmer nightside. It is within the deep, dark oceans of a Hycean eyeball that the potential for life becomes truly intriguing. The high pressure and absence of light at depth are no barrier to life. We see this in the deepest trenches of Earth's oceans. The combination of a vast, liquid water environment, natural chemical energy sources from the planetary interior, and the protective, warming hydrogen atmosphere creates a long-term stable environment. Life here would not be based on sunlight but on chemosynthesis, thriving around hydrothermal vents on the deep seafloor, completely independent of the fixed star above. The entire global ocean, connected from the warm dayside to the cold nightside, could act as a conduit for the spread of such life, with deep currents slowly circulating microbes and nutrients across the globe. The Hessian eyeball, therefore, represents a hidden oasis, a world where the eyeball configuration drives a global ocean, but where a thick atmosphere and immense water volume create a potentially habitable environment that is both alien and, in its own way, more globally interconnected than its rocky counterpart. Beyond these two, the gallery of exotic eyeballs is limited only by the variety of planetary building blocks. We can theorize a snowball eyeball, which is what you get when the ice albedo feedback wins its war against the greenhouse effect, encasing a world in global ice, but with a slightly thinner, more transparent ice layer over the dayside that allows a subsurface ocean to be warmed, creating a faint, diffuse blue pupil beneath the icy surface. Or consider a carbon eyeball world, formed in a carbon-rich system where the dayside might host a vast, tarry ocean of hydrocarbons like those speculated to exist on Saturn's moon Titan, but on a global scale with its nightside a frozen landscape of organic compounds. Each of these theoretical worlds pushes our understanding of planetary science and redefines the boundaries of the habitable zone. They demonstrate that the eyeball configuration is not a single, specific environment, but a fundamental planetary archetype, a common outcome for worlds orbiting the most common stars. Whether the staring eye is one of water, lava, or hydrocarbon sludge, it represents a powerful and recurring theme in the universe, the permanent, beautiful, and often brutal signature of a world held in the unwavering gravitational embrace of its star. Yet as we contemplate reaching out to touch these distant worlds, we must also pause and ask ourselves a difficult and deeply ethical question. What right do we have to interfere? The moment we send a probe, or one day a human crew, into the atmosphere of an eyeball Earth, we cease to be mere observers and become active participants in its story. The principles of planetary protection, long established for our solar system, would face their greatest test on a world that might host an entire, independent biosphere. The stakes are almost incomprehensibly high. A single microbe hitchhiking on a spacecraft that wasn't sterilized with absolute perfection could become an invasive species on a cosmic scale. On the dayside, an Earth-born bacterium thriving in the warm ocean could outcompete and completely extinguish native photosynthetic organisms that have evolved over billions of years. In the specialized ecosystems of the Terminator, a foreign fungus or virus could unravel a fragile food web in a matter of decades. Even on the frozen nightside, a resilient extremophile from our own deep sea vents, introduced into the subsurface ocean, could disrupt the delicate chemical balance that sustains a hidden biosphere. The contamination would be irreversible. We would have forever altered or even erased the very life we sought to discover, committing an act of unintentional but colossal genocide across an entire planet. This leads to a profound philosophical dilemma about the intrinsic value of alien life, regardless of its intelligence or complexity. Is a world only worth preserving if it hosts creatures we recognize as conscious or intelligent? Or does a planet teeming with microbial mats, strange chemosynthetic worms, and vast forests of twilight algae possess a value all its own, a right to exist and evolve on its own terms, free from our interference? If we discovered an eyeball Earth with a biosphere at a stage analogous to Earth's own Precambrian era, a world of simple but widespread life, would we see it as a precious, living laboratory to be observed from a distance, or as a new frontier to be claimed and settled? Our history on Earth offers a sobering lesson. Human exploration has repeatedly led to the introduction of invasive species that devastated native ecosystems, from rats on island nations to diseases in populations with no immunity. On an interstellar scale, our failure to apply those lessons could have consequences that echo for eons, making us the architects of a galactic extinction event. The ethical imperative here is one of humility. It forces us to recognize that we may not be the owners of the cosmos, but simply one form of consciousness among many, with a responsibility to act as stewards, not conquerors, as we step into the larger universe. This stewardship extends to the very methods we use to explore. The current protocols for sterilizing spacecraft bound for Mars are stringent, but they were designed for a world that appears largely dead. For a living eyeball Earth, we would need to develop entirely new levels of biocontainment, perhaps even the concept of completely sterile, disposable probes that make no physical contact with the environment, using remote sensors and lasers to conduct their analyses from the safety of orbit. Any notion of human landing would present an even greater challenge. A single human breath contains thousands of microbial species. Our bodies are walking ecosystems. Establishing a habitat on the Terminator line, no matter how sealed, would inevitably lead to leaks and contamination over time. The only way to guarantee absolute planetary protection might be to forego landing altogether, to accept that some worlds are for looking, not for touching. This would require a monumental exercise in self-restraint, especially if the planet held resources vital for our own expansion, or if it presented the first clear evidence of complex alien life. The temptation to get a closer look would be overwhelming, pitting our insatiable curiosity against our ethical duty to preserve the pristine. And what of the opposite scenario, the potential danger to us? The field of astrobiology must also consider the remote but real possibility of backward contamination. While the ecosystems of an eyeball Earth would be so alien that their biology might be entirely incompatible with ours, we cannot assume that. A pathogen from the dayside ocean, using a biochemistry similar enough to our own, could theoretically find a host in a human explorer or, even worse, be brought back to Earth with catastrophic consequences. This risk, famously explored in fiction, adds another layer of ethical and practical complexity. It suggests that our first missions to these worlds may need to be one-way trips, not just for the probes, but for any samples they collect, analyzed in isolated, high-security laboratories in deep space, far from both the target planet and our own home world. Our responsibility is therefore twofold: to protect them from us and to protect us from them, creating a double-walled quarantine that acknowledges the profound and unknown power of biology evolved in complete isolation. Ultimately, the way we choose to approach an eyeball Earth will define us as a spacefaring species. Will we be the careful archivists of the galaxy's biodiversity, or will we be the bull in the cosmic china shop, spreading our own biological footprint wherever we go? The decision cannot be made by a single nation or corporation. It must be the subject of a global and perhaps eventually interstellar conversation, guided by scientists, ethicists, and philosophers. The discovery of a living world around another star would be the most profound moment in human history, a revelation that we are not alone. Our response to that discovery will be equally profound, a test of our wisdom, our maturity, and our capacity for reverence in the face of the incredible, delicate tapestry of life that the universe has woven. The silent, staring face of an eyeball Earth challenges us not only to see it, but to see ourselves clearly, to decide what kind of neighbors we will be in the vast and living cosmos. To understand the true significance of these staring worlds, we need to zoom out from individual planets and see them as part of the grand, unfolding story of our galaxy. The formation of any planet is a chaotic and violent process, beginning within the swirling disk of gas and dust that encircles a newborn star. In this cosmic nursery, dust grains collide and stick together, slowly building pebbles, then rocks, and eventually planetesimals, the building blocks of worlds. For a terrestrial planet like an eyeball Earth, this process culminates in a final, violent stage of giant impacts where these embryonic bodies smash together to form a few large worlds. The specific characteristics of the final planet, its size, its composition, and crucially, its water content, are a direct result of where it forms within this protoplanetary disk and the specific history of collisions it endures. A planet that forms farther out beyond the system's snowline, where water can exist as ice, might accrete a vast reservoir of water before migrating inward. This water-rich start is the essential prerequisite for a classic eyeball Earth. Without it, you might get a lava eyeball or a barren rock, but not a world with a liquid ocean iris and a frozen ice sclera. This means that every eyeball Earth we discover is a fossilized record of its own violent birth. Its very existence tells us a story about the conditions in its primordial disk. The presence of a massive surface ocean suggests it formed in a water-rich environment, or that it was bombarded by water-bearing comets and asteroids late in its formation, a process known as the late veneer that is also thought to have delivered much of Earth's water. The planet's location, tidally locked in the habitable zone of a red dwarf, speaks to a relatively calm and stable orbital history after its formation. If it had undergone dramatic gravitational interactions with giant planets, it could have been ejected from the system entirely or thrown into a wildly eccentric orbit. In this way, these planets are like time capsules. By studying their bulk properties, their density, their orbital configuration, we can work backwards to understand the architecture and composition of the infant planetary system they came from, piecing together a narrative that began billions of years ago. The prevalence of eyeball Earths also forces us to reconsider the very timeline of planetary evolution and the potential for life in the cosmos. Our Sun is a middle-aged star, and Earth took nearly 1 billion years to cool, form oceans, and see the first flickers of life. Red dwarf stars, however, are incredibly long-lived. A planet like Proxima Centauri b could have settled into its stable, tidally locked state and developed its eyeball climate within its first few 100 million years. And because its parent star will shine for trillions of years, that climate could remain stable for an almost incomprehensible period. This presents a staggering possibility. Life on an eyeball Earth could be billions of years older than life on our own planet. While complex, intelligent life might face the barriers we discussed earlier, simple microbial life could have had an unimaginable head start. The galaxy could be filled with ancient, stable biospheres on these worlds, ecosystems that have been quietly evolving and diversifying in their permanent light or eternal dark since a time when Earth was a lifeless, molten rock. The search for life on eyeball Earth, therefore, is not just a search for our contemporaries, but potentially a search for our universe's most senior inhabitants. Studying these extreme environments also provides a powerful lens through which to view our own planet's past and future. Earth has not always been the temperate, rotating world we know today. Geologists have found evidence that our planet may have experienced its own snowball Earth episodes, periods where the entire globe, or most of it, was encased in ice. While not tidally locked, a snowball Earth represents a similar climate extreme, a planet where the ice albedo feedback ran rampant. Understanding the delicate balance that prevents an eyeball Earth from tipping into a permanent global ice ball helps us model what might have pulled our own planet out of those deep freezes, likely a combination of volcanic outgassing of greenhouse gases and the slow, steady warming of the sun. Eyeball Earths serve as a controlled laboratory for studying these climatic tipping points, showing us the conditions under which a planet can become largely frozen, and crucially, what it takes to maintain a pocket of liquid water against the relentless pull of global ice. Looking to the future, these worlds also offer a glimpse of Earth's ultimate fate, albeit on a vastly different timescale. our Sun is steadily increasing in luminosity as it ages. In about 1 billion years, this increased energy output will likely trigger a runaway greenhouse effect on Earth, evaporating our oceans and transforming our planet into a scorching, Venus-like hellscape. Long before that, however, the habitable zone will have migrated outward, but for a planet like an eyeball Earth orbiting a stable red dwarf, the habitable zone remains fixed for eons. Their future is one of remarkable stability. This contrast is profound. While Earth is a temporary oasis with an expiration date, an eyeball Earth could be a near-permanent haven, its climate maintained by the steady, frugal glow of its star for timescales that dwarf the current age of the universe. They represent a model of long-term habitability that is completely different from our own, a lesson in cosmic endurance versus our own planetary transience. Ultimately, placing eyeball Earths within the cosmic context transforms them from mere curiosities into essential characters in the story of planets. They are not freaks of nature, but rather a common and perhaps even dominant outcome for worlds orbiting the most numerous stars in the galaxy. Their study bridges the gap between planetary science, astronomy, and astrobiology, forcing an interdisciplinary conversation about how worlds form, how climates stabilize, and how life might arise under a completely different set of rules. Each one we find adds a new data point, a new piece to the puzzle of how diverse planets can be. They challenge our Earth-centric assumptions and expand our definition of a habitable world, teaching us that the universe favors a spectrum of environments, from the dynamic and cyclical to the permanent and extreme. In their silent, staring faces, we see reflected not just the light of their stars, but the incredible breadth of planetary possibility, a reminder that our own world is just one verse in a much longer and more varied cosmic poem. And so we arrive at the end of our journey, having ventured across the stark and beautiful landscapes of these cosmic eyeballs. What makes them so uniquely captivating is not just one single feature, but the powerful convergence of extremes that defines their very existence. They are worlds of profound duality, where the concept of a day is replaced by the permanence of geography, a blazing, aquatic hemisphere locked in an eternal embrace with its star, and a frozen, lightless wilderness that gazes forever into the void. This stark contrast isn't a flaw. It's a masterpiece of gravitational physics, a stable and long-lived climate state that challenges our very definition of a habitable world. The potential for life on such a planet is what truly ignites our sense of wonder, forcing us to consider biology not as a fragile phenomenon requiring Earth-like conditions, but as a tenacious force capable of exploiting any available energy gradient. From the hyper-specialized photosynthesizers of the sun-drenched ocean to the chemosynthetic communities thriving in the absolute darkness of a subsurface sea, these worlds teach us that life's strategies are as diverse as the cosmos itself. In the grand endeavor of modern astronomy, eyeball Earths have moved from speculative fiction to central players. They are natural laboratories that test our most sophisticated climate models and refine our search for life beyond Earth. By studying their atmospheric compositions, their thermal maps, and their bizarre weather patterns, we are not just learning about distant exoplanets, we are stress-testing the fundamental principles of planetary science. These staring worlds have fundamentally rewritten the rules of the habitable zone, demonstrating that the most common real estate for life in our galaxy likely exists under a fixed and unmoving sun. This realization shifts our entire perspective, turning our gaze toward the quiet, dim red dwarf stars that dot the sky, each one a potential host to a system of these extraordinary planets. The ongoing and future missions, from the James Webb Space Telescope to the planned Habitable Worlds Observatory, are poised to transform these faint points of light into worlds we can truly begin to map and understand, bringing the mysterious eyeball Earths into sharp, breathtaking focus. As we conclude, I want to leave you with a final thought, a call to your own imagination. The next time you find yourself under a clear night sky, look up at the twinkling tapestry of stars. Pick out a faint, reddish pinprick of light, one of those ubiquitous red dwarfs, and for a moment allow yourself to envision the world that might be orbiting there, a majestic celestial marble, half brilliant blue and half gleaming white, suspended in the eternal quiet of space. Picture the churning, warm ocean under the permanent star, the towering glaciers of the dark side, and the narrow, life-giving ribbon of perpetual twilight in between. Contemplate the possibility that within that delicate balance of fire and ice, an entire saga of alien life could be unfolding, completely independent of our own. This isn't just a daydream, it is a very real possibility supported by our current understanding of the cosmos. The universe is far stranger, more diverse, and more creative than we ever dared to imagine, and it invites us to keep looking, keep questioning, and keep wondering. The greatest journeys of discovery are still ahead of us, and they begin with a simple act: staying curious. If you enjoyed this voyage to the frontiers of science and imagination, we would be thrilled to have you join us for the next one. Thank you for watching, and never stop looking up.